Hello, welcome back. In this lesson, we shall talk about integers, matrices, and arrays. So the name Matlab actually means Matrix Laboratory. So it's all about matrices when it comes to Matlab. We're going to see how to use matrices and how they are different from arrays or whether they are the same. Before we do that, let's clear our screen over here. I'm just going to type CLC like this. So first and foremost, you must know that all Matlab variables are multidimensional arrays, no matter the type of data. Let's see what I mean. For instance, let's say we have a variable x equals, into bracket, 1, 2, 3, 4, 1, 2, 3, 4, and we hit enter. This is x. We can observe that x over here is a matrix with a single row and 4 columns. This is the first column, the second column, the third, and the fourth. Or we can also call x a row vector or a matrix. So to create the same matrix with two rows, we can simply type x equals, and when we type x, we overwrite in the previous value of x. So we're creating a new x. We can simply say x equals, and then come back 1, 2, 3, 4. So this is the first row. To create the second row, simply put a semicolon like this, and then we can say 5, 6, 7, 8, and we hit enter. And as you can see, now we have 2 rows, 4 columns. Each row is separated by a semicolon, and each column in a row is separated by a comma. So we have 1, 2, 3, 4, semicolon, 5, 6, 7, 8. Hence we have row number 1, row number 2. So this is how to create a 2x4 matrix. So this is how to create a 2x4 matrix. We first type the values of the first row separated by commas, and then once we are done typing the values of the first row, we put a semicolon and then type the values of the second row separated by commas as well, like this. Also, there are built-in functions for creating things like zero metrics. For instance, let's say we want to create a matrix of a particular size filled with zeros. Let's say we want to create a 5x5 matrix with all values filled with zeros. We can say z equals, and then we call the function zeros, and then we pass the argument 5, 5 and hit enter. And as you can see, we've got 5 rows, 5 columns, all with zeros. As simple as that. In the same way, if we just wanted a 2x2 matrix filled with zeros, we could just say z2 equals zeros, 2, 2, and we have a 2x2 matrix over here filled with zeros using the zeros command. Very useful. In the same way, there is a function for creating ones. Imagine you want to create a matrix with all of the values set as 1. We can say, let's say q equals ones, the function is called ones, and then the first argument is the number of rows, and the second argument is the number of columns. This time, let's say we want just 1 column, so I could just put this here, and we have this. So q equals 5 rows, 1 column matrix. In the same way, we can go back to our 5x5 example with all ones like this, and then we have a 5x5 matrix with all 1. As simple as that. And just like in algebra class, we can add a value to we can add the same amount or the same value to all the members of the matrix. For instance, let's say we want to add the number 20 to each and every member of the matrix Q. So we can simply say Q plus 20 over here, Q plus 20 like this. And as you can see, the answer is 21. So now we have a 5x5 matrix with all values set as 21. In the same way, we could say Q divided by 1 or Q. We can use any arithmetic operation actually. So I'll just say Q2 over here equals Q times 10. How about that? Q times 10 like this. Sorry about that. Q times 10. All of the values are at 10 now, and then we can come here to say Q2 divided by 2, and all of the values are divided by 2 now. Perform simple operation on the matrix. In the same way, we can create a trigonometric matrix from the current values of Q. We can simply say Q3 equals sine Q2. So it's going to find the sine of 10 and place it in all the values. As simple as this, and this is what we have. Really, we can perform any operation all at once on all the values of the matrix using these methods. So in the same way, there's a built-in function for creating a magic square matrix. So a magic square matrix is a matrix in which all the rows, columns, and diagonal add up to the same value. So let's see how to do that. To create a 5 by 5 magic matrix, you can just say magic. I'll just give this a new variable. Let's call this capital M, and then I'll say magic, and then we want a 5 by 5 magic matrix. As you can see, this is it. And then to find a transpose of a matrix, all we need to do is we need to use a single quotation mark. Let's say we want to find the transpose of M over here. M is a magic matrix, and we can say small m over here, or we can say M underscore transpose. Now let's start using proper variable names in order not to confuse ourselves. And we can say it's as simple as M and this. And when we do this, we have a transpose. And a transpose basically transforms all rows into columns, or transforms all columns into rows. So that's what a transpose does. And we can do that simply by calling the name of the matrix with a single quotation mark like this. And as you can see, this row over here, 17, 24, 1, 8, 15, has been transformed here to a column 17, 24, 1, 8, 15. We can also find the inverse of the matrix by using the INV command. Let's see what I mean. So I could say capital I over here equals INV of M, and I hit enter. And then this is the inverse of this matrix over here. Also, we can change the data type of the result. So now the result is printed in a short format. And a short format is usually a 16-bit, sized data type. We can go to a 32-bit data type, which is a long. And to change the format, and by changing the format, it's going to increase the resolution of the result over here. To change it to a long, we can just use the format command. We can say format long like this, and then compute the inverse of the matrix again. And now, as you can see, the data has higher resolution. And to change it back to the short format, we can just say format short, and then compute again. And then we're back to the short version of it. As simple as this. Also, I should point out that the format applies only to the display of the result. It does not affect the computation of the result. The result is computed quite accurately and precisely. If we want to display the result in a high resolution, that's where we call the format long to give us all these long numbers. And if we want in a shorter version, losing some part of resolution, we can just go to format short, as simple as that. Hello, welcome back. In this lesson, we shall look at matrix concatenation. So before we begin, let's just clear the screen. I'll just type CLC over here, and let's say we have a matrix which is let's say a 3 by 3 matrix. How about that? So 1, 2, 3 semicolon 4, 5, 6 semicolon 7, 8, 9, and we hit enter. So we end up with a 3 by 3 matrix. So let's say we have this matrix and we have another matrix. Y equals, how about let's just use the zeros, yeah, or the ones. Let's just use a 3 by 3 matrix, all of 1. So I can just say ones 3 by 3. So Y equals this. We have this. Let's say we want to concatenate, want to add these two matrices together, and want to add them horizontally. We can just say Z equals and open a square bracket here like this and say x like this, comma y. And this is what we have. We have them concatenated. In the same way, if we had used y as the first argument and x as the second argument, we would have had the y matrix appearing on the left side and the x appearing on the y side. Let's see what I mean. We can say z1 equals y comma x, and this is what we have. So this is what is known as horizontal concatenation. So if we want to perform a vertical concatenation, we simply need to replace this comma over here with a semicolon. So let's see what the current concatenation looks like. It's a horizontal concatenation, and what happens is the number of rows remains the same, just the amount of columns increase. So all of them have 3 rows, 3 columns. When we concatenate them, it becomes 3 rows, 6 columns. But with vertical concatenation, the amount of rows will increase and the number of columns will remain the same. So let's concatenate x and y vertically and see what happens. So I'm going to create a variable v, and I'm going to say v equals square bracket x semicolon y, and this is what we have. This is the vertical concatenation. Very simple, very straightforward. So in the next lesson we shall see how to deal with complex numbers, and I shall see you in the next lesson. Hello, welcome back. In this lesson we shall see how to represent and work with complex numbers. And as you may already know, complex numbers have a real part and an imaginary part. So to begin, let's just clear the screen by CLC. For example, we can get a complex number just by computing the square root of -1. So I could just say, I'll give a variable x equals sqrt, which is the command for computing square roots, and then -1 over here. And as you can see, this x variable has two components. It's got this one here and then this one here. This is the real part, and the real part is all 0 is 0, and the imaginary part is 1. And the imaginary part is indicated by the I over here. So this is a complex number. So we can create another complex number, y equals sqrt -g, like this. Sorry, I mistyped this. sqrt like this. And we have these two complex numbers. To add them, we can simply say z equals x plus y, and then it would perform the complex addition for us. As you can see, this is what we get when we add these two numbers. Very straightforward. Right. Hello, welcome back. In this lesson, we shall see how to access the array members at different locations, or the matrix members at different locations, and this is known as array indexing. So like always, let's clear our screen with CLC, and let's just create how about a 5x5 array? How about a magic? We use the magic square matrix, which is we generate a 5x5 magic square matrix. Let's say M, capital M equals magic into bracket 5, and we have this 5x5 matrix. So let's say we want to know what is at the row number 1, column number 4. Let's say this is in our code and we want to locate what's at this particular location, row 1, column 4, which we know this is row 1 and this is the 4th column. We can simply say, we can store it in a variable such as x and say x equals m row 1, column 4, like this, enter. And as you can see, this is 8, because this is row number 1. This is row number 1, this is column number 4 of row number 1. In the same way, we can say x2 equals m, which is the name of the matrix. And let's say we want to find row 2, column 1, so we can say 2, 1 over here, and we expect to get 23. And as you can see, this is 23. So this is how to use the this is how to get a value in the array. And we can actually create a function to loop through all the values, which we shall see later. So as we know, this is a 5x5 matrix. If we try to access something outside the 5x5 range, the system will throw an error. Let's say I say x6 equals x3 equals, matrix M access row 6, column 1. I hit enter. This doesn't exist. Therefore, I'm getting this error. So whenever you get this error, it means you are trying to access something in the array that is out of the boundary of the array. Basically, it says index in position 1 exceeds array bounds, must not exceed 5. So basically, position 1, this one here exceeds the number of rows that we have. Also, we can access a range of values. So suppose we want to access the values located at the second row, columns 2 through column 5. Let's see how to go about that. Let's say we create a new variable v equals, and then we want our matrix M. We want to access row number 2, which column? We want column 1, and then we use colon access from 1 through 5, just like this. So when I hit enter, this is what we have. These are the values at row number 2 from column 1 to 5. As you can see, this row number 2, this is row number 1, row number 2, this row number 2, column 1, column 2, column 3, column 4, column 5. We can, in the same way, say row number 2 from column about 3 to 5, just to shorten it a bit. And as you can see, we've got 7, 14, 16. This is how we can access a range of indices, if you may, all at once by using this method here. The first parameter or the first argument is the row number, and the second argument is the column number. Okay, so pause the video and then try to access from rows number 2 to 4, column 5. You want to access the values between rows 2 through 4 at column number 5. So pause the video and try that. Row 2 to 4, column number 5. Okay, let's see what you did. So I could just say v2 equals, and then our matrix is M, and we're saying row 2 to 4. We write it like this, comma, column number 5, and we hit enter. And as you can see, row 2, what is row 2? This is row 2 to 4. Column number 5 is located over here. So we have row 2, row 3, row 4. And all of them are in column number 5. Hence we have 16, 22, 3. So this is how to access a range of rows as well. It's very simple. It's the same thing we did for accessing a range of columns. It's the same thing here. So this is it. So that's all there is for this lesson. If you have any questions, just send me a message or leave in the questions section. And I'll see you in the next lesson. Hello, welcome back. So in this lesson, we shall see how to save our variables. So throughout the lesson so far, we've generated a number of variables here. As you can see in the workspace, it's showing all the variables. To get information about the variables we have here, we can use a simple command known as whos, W-H-O-S, as simple as this. And this one here gives a description of all the variables. It gives their size, the number of bytes they occupy, and the data type, which over here is known as class, and any special attributes they may have. For instance, this one over here is a complex number, therefore it says complex here, and all our variables so far have been double, they've been of type double, and these are their sizes. We use the whos to check our variables. In the same way, we can click them individually, and then they will open, and this is it. Individually, we can click to observe each variable. So this is a matrix, this is a 5 by 5 matrix, so it's showing us the matrix here. And we can just click to open them, or we can just use whos to get a description, a summary of all of them. So if we close Matlab, we would lose everything here, all these variables. In order not to do that, we can save these variables in a file. And to do that, we use the save command. So we can simply say save, and we give the file a name. So I can just say my var for variables, and then we have to save it to .mat, M-A-T format, .mat like this, and then I'll hit enter. And as you can see, it's appeared over here in my project folder. So these variables have been saved into my project folder. Anytime I can import these variables and then continue from where I left off. As simple as that. So far, we've learned how to clear the command window. We use the CLC to clear everything here. We can also clear all the variables and get rid of them. There's another command, and this is known as declare all. So if I type clear all, you can see everything disappears. All the variables in the workspace have disappeared. And then I can do CLC to clear my command window as well. As simple as this. And it's all nice and clean now. So now if we try to access our variables that we had, like V and Z, for instance Z, as you can see, it doesn't exist. We use X a lot. It doesn't exist because we don't have it in the workspace. We've essentially deleted them from the workspace. So fortunately, we save the variables, and to load these saved variables back into our workspace, we can use the load command. We can simply say load myvar.mat, and as you can see, we have our variables here. Now if I type Z, I've got a value of Z, it's a complex number. If I type X, I've got a value of X, it's number 8 over here like this. Very simple, very straightforward. This is X, it's 8. So this is all there is for this lesson, and as usual, if you have any questions, do send me a message or leave it in the questions section, and I shall see you in the next lesson. Hello, welcome back. So in this lesson, we're going to see how to plot 2D graphs with Matlab. So if you have anything in your command window, you can clear by typing CLC like this. And if you have anything in your workspace, if you have the variables from the previous lesson over here, you can clear them as well by typing clear all like this. But I've got nothing here, so there's no change at all. So in order to plot values, you need values to plot, isn't it? So we're going to generate some values, and what we're going to do is we're going to create an array called X, and the array ranges from 0 to 2 times pi. So we start by declaring X equals 0 colon, this is the beginning value, and then 2 times pi. Once we do this, we have to indicate the step between each value in the array. So now we just say we want an array of values between 0 to 2 times pi. Do we want each value to be separated by a value of 1, a value of 2, or a value of 3? So to indicate the step between each value, we can just come over here, put another column, and put a step over here, the step between each value. And we want them to be separated by pi divided by 100, like this. As simple as that. And in order not to display all the values, we just put a semicolon here, click and hit enter. And as you can see, we have this here. We can view X if we want, and this is X. We've got 0, start from 0, and we've got 1 row, 201 column element. Basically, that's what we have. So now this is our X value. So we can create a sinusoidal function by computing the sine of X. Like this, we can say y equals sine x, and then we have this as well, and as you can see, it's the same size as x. And now we have the xy values. We can use the inbuilt plot function to plot this sine wave. We can say plot x y like this, then we'll hit enter. Sorry, I said W. I wonder why I did that. Plot XY like this. And as you can see, this is our sine. Like this. If we zoom in, you would see the demarcations. To zoom in, you click over here, and then you select a part that you want to zoom into. I could just zoom into this tiny bit, and then it zooms in, and then we can zoom further, keep zooming further, like that. Can zoom back out. So this is how to plot 2D graphs. Very straightforward. Currently our graph shows no label. In fact, there's no information here at all. So we can add some labels here. We can label the x-axis as well as the y-axis, and then add a legend to the graph. So let's do that. We can use the inbuilt x label function and y label functions to do that. So I could come here and say x label, and we can call this x values over there. Can say y label as well, y label, and then we call this y values. So to put it all together, let's start again. We plot x, y, This is xy. Then we add the x label. We're calling it x values. And as you can see, it's been added here, x values. And we add the y values, which is actually sin x. But you know that already, so I'm not going to add that. As you can see, it's over here. In order not to always click and show the graph, we can use the SGH function. We can use the SHG function, sorry, and then the graph would always show up like this. We can also add a title. We can call title and give it a title, and the title of this is, we can say sine plot, as simple as that. And then we can call SHG again. As you can see, it says sine plot here, x values, y values. Very simple. Also, we can format the line color and the line type. We can define a symbol to be used in plotting the line. So we can come here, plot. The plot accepts a third argument as well. Then this third argument, we can say R for red. Let's see what happens. SHG. As you can see, the line is red. In the same way, we can say B for blue, and SHG, the line is blue. We can try green, SHG, and the line is green. Right. We can also decide to plot the line using short dashes rather than having all of it connected together. Rather than it being a continuous line, we can make it into short dashes. And let's see what I mean. We can say plot green using the symbol. And let's see. Sorry. Now this is what we have. We can also say plot green using this symbol. Sorry about that. And let's see what we have. Sorry. And this is what we have using the asterisk. So we can zoom in to see that indeed is that symbol. So we're using dash asterisk to plot the line. It's disappeared. I'll bring it back like this. Very simple. Hello, welcome back. So in this lesson, we're going to see how to display multiple plots in the same window. So this is my Matlab. I already cleared the command window, and then I saved the variables we used earlier. So I saved them. We still have the XY arrays here. Remember the XY arrays we created. I hope you still have yours. If you still have your command window saturated with too much information, you can just use the CLC command to clear everything and still keep the variables in the workspace like this. So let's go on. In this lesson, we're going to use the hold on and hold off commands. So before we proceed, let's just draw our graph again. I've cleaned mine, so I'll just plot XY again. I'll plot it in its default settings, which would appear as blue. So I'll just say plot X, Y, and this is XY. So suppose we want to add another plot to the same figure over here. We can just use the hold on command, hold on, like this. And then let's create Y2. We can say Y2 equals the cosine of X, as simple as this. And Y2 is created here. So now we can simply say plot X values with Y2, and we can plot this as color green. We can pass the parameter R over here. Let's see. As you can see, we've got the cosine of X plotted in the same figure. It's because we use this hold on command. Without the hold on command, we'd have plotted in a new figure. And we can keep adding things to the figure until we use another command known as the hold of command. So we can add a legend to the current figure. So we can just use the legend command here and say legend, and we know our first plot is a sine, so we can just give it a name sine, and the second one is a cosine, so we can call this cos. And when we're done, we can just say hold off like this. And now, do you remember the command we used to bring the figure in front of the window? You know it's hidden and I need to press here to show it, but we can use another command. So just for a quick test, do you remember that command? It's a 3-letter command. Well, you probably remember it is SHG. So we use SHG and then we have this here. So this is it. We've got two plots in the same figure. The first one, we've got a legend here as well. The first one is sine, the second one is cosine. Very simple, very straightforward. So this is all there is for this lesson, and I shall see you in the next lesson. Hello, welcome back. In this lesson we shall see how to handle missing data, how to deal with missing data in the data set. So to begin, let's first examine how to create some form of missing data and then see how we can deal with the particular set of data that is missing data. I know I've said quite a lot of missing data. Bear with me here. So I'll just clean the command window with CLC, and then I'll clear the workspace as well. We clear all like this. Right. So let's create an array of variable x. So I could have x equals, I can say 1, 2, 3, 4, and NaN. NaN here is a built-in command to create missing data. And then I can say 6, 7, 8. When I hit enter, we have 1, 2, 3, 4, NaN 6, 7, 8. So this is one way of creating missing data. In the same way, we can create missing data using the word missing. So we can have a data, an array like this. Can say 10, 11, 12, 13, missing 89. And let's see, 10, 11, 12, 13, just by using the word missing, let's replace it with the missing data notation, NaN. Let's see what happens when we plot an array containing a missing data. So let's plot x over here and see what happens. So I'll just say plot x. Remember, x has the values 1, 2, 3, 4, missing data 6, 7, 8. So I'll just plot this, and this is what we have. We've got 1, 2, 3, 4, and then there's this chunk here omitted, and then 6, 7, 8. So this is what happens when you plot missing data. Okay, let's observe some more interesting characteristics. So suppose we want to find the mean of this array. The mean of x, we just plotted x, and x over here is plotted this way, showing that there is a missing data value over here. So let's say we want to find the mean of x. Mean of x, like this. The answer is NaN. Why is that? Because NaN could be any value. Therefore, Matlab is not able to compute the mean for you. How about we try the max? We try to find the maximum value in the array x. So max. However, over here, max returns the maximum number. So this is the characteristics of this array. This is how Matlab treats an array with missing data. When you're trying to find the mean of the array, you receive an NaN. However, when you're trying to find the max, you get the maximum value in the array. Let's find the minimum value of x and see what behavior we get. And indeed, we get a minimum value. So with all other statistical computations, we can derive them accurately, ignoring the missing data. However, when we try to get the mean of the array, it returns NaN. Let's see the variance as well. If we try to plot the variance, if we try to get the variance of the array, it returns NaN as well. How about the standard deviation? Let's see the STD. That's NaN as well. Right. So this is how the array behaves. This is how an array with a missing data point behaves in MATLAB using the simple MATLAB built-in functions. Also, there's a way to check if there is a missing value in an array. We can use a function known as isNaN, as simple as this. And this function takes the array as the argument. So we can say isNaN and then pass the array we want to check. Let's use x here. And then it returns 1. This is the location of the missing value. So in essence, it's saying the very first value is not missing, the second isn't, the third isn't, the fourth isn't, but the fifth point is a missing value. As you can see over here, number 5 is missing. Where is it? It's over here. Number 5 is missing. And remember, x is a 1/8 matrix. You can think of an array as a matrix with a single row. So it's telling us that number 5, column number 5 has missing data there. So we can use the is missing, we can use the isNaN to check whether an array has a missing data or not. In the same way, we can use the more literal way, which is the command is missing. We can say is missing. It's another built-in command, and this one also just accepts the array as the argument. So it's missing x, and it returns the same result, just like NaN. So we can replace the NaN values, the missing values. We can set our own value if the data has any missing value in it. There's a fill NaN command that we can use. So we can just create another variable here. Let's create another variable called x2. x2 equals, the command is fill missing, and then this one here takes 3 arguments. The first one, we fill in array x, and we want to fill it with a constant, and we want to replace any missing value with the value 1. So any missing data in array x is going to be replaced with a constant 1. So we can hit enter. Now let's see what x2 is. As you can see, the position of the missing data is replaced with 1. So if you have a large data set, there's a simple example. By margin, you have a data set, you have an array of 2,000 members. You can simply use this command to replace all missing data points, like this. And now we can perform the statistical computation we couldn't perform at first, like STD. We can find the standard deviation of x2, and it should be a value returned to us, 2.7. We can find the mean of x2. And in the same way, we can find the variance of x2. Right. So there's another option. If we do not want to replace the missing data with a constant value, we can remove it, and we can use the rm missing command. So let's have x3 here, and x3 equals rm missing, and we can pass x here, and as you can see, it's taking out the missing data, and it's shortened the of course it's shortened the size of the array. So the array size is now -1. So x3 is 1 short, shorter than x. X here has 9 members. x3 has just 8 because we deleted the missing data using the rm missing command. So this is another way of dealing with missing data. You can delete it all at once. If you have a large data set, 2,000 members, 5,000 member array, you can still use this command, and then it will just delete all the missing data points. So this is all there is for this lesson. If you have any questions, do send me a message, yeah? And I shall see you in the next lesson. Hello, welcome back. In this lesson, we're going to see how to write data to a CSV file. CSV is basically comma separated file. We're going to see how we can export our data into such a file. So this is my MATLAB. It's opened. I've cleared the screen. You can type CLC to clear your screen as well. So what we're going to do is we're first going to create a simple sine wave, and then we plot the sine wave. We see what it looks like. Then we store the sine wave's data in a CSV format into a .txt file. Then later on, we're going to read this file back into Matlab and plot it. This will just show us how to write to and read from files. So let's say we're creating a signal of frequency 20 Hertz. I'll just put a variable f over here. F equals 20. Let's say we want the sampling frequency to be 100 Hertz. We can define sample period Ts over here equals 1 over 100. And then let's say we want the signal length to be 3 seconds. We can say capital T equals 3. And then we can create the x-axis interval by saying t here, small t equals 0 colon ts colon t. So basically our signal runs from 0 to 3 seconds, and the step between each value is ts, 1 over 100 over here. And then I put a semicolon here. So then we can call the signal y. I can say y equals sine into bracket 2 times pi times f times t, and we have the signal. So we can plot the signal by saying plot. So we can either say plot y or plot ty, and t will represent the x-axis value and y will be the y-axis value. So I'll plot the signal. Let's see what it looks like. So this is our signal, 20 Hertz signal. I've zoomed in. Just click back here to zoom out. Right. So as we know, this signal is just an array. This is it. We can double click here to see what's in y. Y is just an array. This is it. These are the elements. It's 301 points long. Right. So let's write this signal to a file. All we're going to do is we use CSV write, which is a function. And this function takes 2 arguments. The first is the file name. If the file doesn't exist, Matlab will create it automatically. So we can say underscore simple signal. Let's just say simple signal. Give it the name simple signal, yeah? .txt. So we have to give the file format .txt, and we are trying to write the content of this vector here, y. So we pass it as the second argument y like this. And we put a semicolon, we hit enter. And as you can see over here, simple signal.txt has appeared in our project folder. So we can just right click and say show in Explorer. And it exists over here. You can double click, and this is the signal. Right. So in the next lesson, what we're going to do is we're going to come back here and then plot the content, read the content of this same file, simple signal, and plot it and see that indeed it's the same. And this will just show us how to write to and read from files. So that's all there is for this lesson. And if you have any questions, just send me a message or leave it in the questions area, and I shall see you in the next lesson. Hello, welcome back. So in the last lesson, we saw how to write the content of a vector to a file. In this lesson, we shall see how to read from a file. And so what I'm going to do is I'm going to say clear all, and this will clear all the variables in my workspace to start afresh like this. Everything here has disappeared. And to clear the things in the command window, I'm just going to say CLC like this, and everything is cleared. So what I'm going to do is I'm going to load the content of simple signal.txt, which we saved earlier, and I'm going to say signal equals load, and then load takes just one argument, the file name, and the file name here is underscore simple underscore signal .txt. Put a semicolon here. So it's going to load the content of this file and store it in this vector called signal for us. So I'll hit enter, and now let's plot signal and see. Plot signal, and it's the same as we saw earlier in the previous lesson. It's the same signal. So that's one way to read from a file, just to use load. Another way to read from a file will be to use the read CSV. Remember, in the previous lesson, we used write CSV to write the comma-separated format to the file. We can use read CSV to read from a comma-separated file. Let's do that. I'm going to say signal2 equals CSV read, and then I'm going to pass the name of the file. It's underscore simple underscore signal.txt, and then put a semicolon here. And once it's finished reading, as you can see, signal 1 and signal 2 here, they have the same length. So let's plot signal 2 and see if it's the same. Plot signal 2, semicolon, hit enter. Yeah, I had a typo in the spelling, so I've been corrected. So this is what it looks like. We've plotted it. So this is how to read from a file. You can either use the load signal or the CSV read. If the CSV read works only with comma separated files, but the load can work with any file at all. If the file was separated by something else, we could use load as well. So that's all there is for this lesson, and if you have any questions at all, do let me know, yeah? So I'll see you in the next lesson.
Hello fellas, welcome back. So statistics and some form of probability are heavily used in DSP applications, mostly for signal characterization. For instance, we often use DSP to reduce interference noise and other undesirable signals in our acquired signals. Statistics and probability are often used to measure and classify these unwanted signals. We define a signal as how one parameter relates to another. That's the simple definition of a signal. Think of voltage changing with time. Since both voltage and time can assume a continuous range of values, this type of signal is known as a continuous signal. When such a continuous signal is passed through an analog to digital converter, the two parameters, voltage and time, become quantized. Signals formed from quantized parameters are called discrete signals or digitized signals. The axes of signal graphs go by various names. The vertical axis represents the dependent variable, and we may call it the y-axis, the range, the ordinate, or the amplitude. The horizontal axis represents the independent variable, and we often call it the x-axis or the domain. In a graph such as changing voltage with time, the voltage is the dependent variable and will be represented on the y-axis, while the time is the independent variable and therefore will be represented along the x-axis. Actually, a more common label for the x-axis is the sample number. We often say the parameter of the y-axis is a function of the parameter of the x-axis. Also, it is very common in DSP to find the letter n used to represent the total number of samples. Each sample is assigned a sample number, or an index as computer programmers will call it. In mathematical calculation, the sample number runs from 1 to n, while in computer programming, the sample number runs from 0 to n-1, because the index of an array starts with 0. So this is the short introduction to this very first lesson, and I shall see you in the next lesson. Hello fellas, welcome back. In this lesson, we shall take a look at some of the applications of statistics in digital signal processing. The mean is defined as the average value of a signal, and it is denoted by the lowercase Greek letter pronounced mu. To calculate the mean, we simply add the amplitudes of all the signals and then divide by the total number of samples. This is represented mathematically like this, where x0 through xn-1 represents the amplitudes of samples x0 through xn-1, and n represents the total number of samples. In electronics, we often call the mean the DC signal, meaning the direct current. The AC refers to how a signal fluctuates around the mean value. If a signal is a simple periodic signal such as a square wave or a sine wave, we can describe its vertical movement by its peak-to-peak amplitude. However, most of the signals we use don't often have a well-defined peak-to-peak. Therefore, a bit of randomness is associated with the signal. This brings us to the idea of standard deviation. Take the expression xi minus the mean, taking the absolute value of this expression. This expression describes how the ith sample deviates or differs from the mean. We can find the average deviation of the signal by summing up the deviates of all the samples and then dividing the sum by the total number of samples. However, caution must be taken when summing up the samples. Note that we are taking the absolute values of each deviation before summing up. If we do not do this, the positive and the negative terms will cancel out and give us 0. The average deviation provides a single number representing the typical distance the sample or the samples are from the mean. The average deviation is not very common in statistics because it doesn't fit well with how nature works. Why is this? Well, when analyzing signals, the important parameter is not how the signal deviates from the mean, but the power represented by the deviation from the mean. For instance, when random noise and signals combine in an electronic circuit, the resultant noise is equal to the combined power of the individual signals, not the combined amplitudes. The standard deviation is similar to the average deviation. The only difference is averaging is done with the power instead of just amplitudes, and we do this by squaring each of the deviations before taking the average. And why does this work? This works because power P is directly proportional to the voltage squared. And as you can see over here, we complete the equation by taking the square root to compensate for the initial squaring. So this is the standard equation of standard deviation. This is the very common equation of standard deviation used across mathematics and statistics. We can also write it in an expanded form like this. Like we mentioned earlier, the standard deviation is the measure of how the signal fluctuates from the mean. The variance measures the power of that fluctuation, and this is the equation for the variance. It's very straightforward. Now let's take a look at the root mean square, the RMS. The standard deviation measures the AC portion of the signal, while the root mean square, known as the RMS, measures both the AC and DC portions. If a signal has no DC component, its root mean square is equal to its standard deviation. So this is all there is to it. Send me a message if you have a question, or you can leave your question below. This is just a short introduction, and I'll see you in the next lesson. Hello fellas, welcome back. In some applications, the mean describes what's being measured, while the standard deviation represents the noise and other interference. In such applications, the comparison of the standard deviation to the mean is more important than the standard deviation itself. This brings us to the idea of signal-to-noise ratio, which is expressed as the mean over the standard deviation. The signal-to-noise ratio can also be measured in another way known as the coefficient of variation. And the coefficient of variation, which is often denoted as CV, is as simple as the standard signal-to-noise ratio, which is the mean over standard deviation times 100. You just multiply 100 by the signal-to-noise ratio, and the signal-to-noise ratio is just the mean over the standard deviation. So that's all there is to it, guys, and I'll see you in the next lesson. Hello fellas, welcome back. So in this lesson we're going to find the mean of a signal. So what I'm going to do is I'm going to clear my command window here by typing CLC. So mostly what you're going to be using Matlab for most of the time is to import a signal into Matlab and then perform some form of signal analysis. So earlier on we exported a signal that we called a simple signal, and we know this signal because we generated it. It's a 20 Hz signal that we generated. So we're going to import the signal, find the mean of the signal, find the variance and the standard deviation. So let's do that now. Let's import the signal. And actually what I want you to do is to pause the video and try to read from the file, import the signal here,
Remember, we learned how to use the load and the CSV read functions earlier on. So I want you to use those functions to import the signal to your command window. Right, I suppose you tried. So let's say we want to import a signal. Let's call this input signal. I'll call this input signal, and I'm going to say input signal equals load, and then the file name is, it's called simplesignal.txt. And make sure you navigate to your project folder. If you navigate properly to your project folder, you'll find the file in your project folder. This is my current folder, and I've got a signal here. It's called simplesignal.txt. It's called, so I'll put the name here, simple_signal.txt. And we can plot the signal. I could just say plot input signal, plot input signal like this. And this is what it looks like. Like I said, it's a 20 Hertz signal, and we generated this. So we're going to find the mean of the signal, and it's very simple in Matlab. It's as simple as using the mean function. So we can create a variable, say sig mean equals mean, and then we pass as argument the signal vector. The signal vector is input signal, so I'll just say input underscore signal like this. And we can print sig mean to see the value. So this is the mean of the signal, right? And to find the variance, we can use the var function. So we can say sig underscore variance var equals var input signal. And we can print the variance sig var like this. And this is the variance. To find the standard deviation, we use the std function. So we can say sig underscore std equals std input underscore signal like this. And we can print it out. We say sig underscore std. And this is the standard deviation of the signal. So to see more statistical functions available to you, we can just type the name of any of these functions and add the word help. It would explain the function and give us more functions in the same category. And let's see what I mean. You can type help std like this. So over here it explains what std is used for and its standard deviation, and down here it gives you other signals like COV, mean, variance, median. So if you want to read more about this, any of these, you can just click, and then this one is about covariance, and this one over here is for correlation. Right, so that is done. I'll just type CLC to clean. So that's all there is for this lesson. This is the very beginning of the course. Don't worry, we'll begin to do much more interesting things later. So that's all there is, and I shall see you in the next lesson.
The signals we encounter in the natural world are continuous. For example, temperature changing with time, brightness of the sun changing with time, voltage changing with time, etc. In order to bring the continuous signals into our computer and work with them, we need to convert them from their analog continuous versions to the digitized discrete version. We use the ADC, the analog to digital converter, to perform this task. The digital to analog converter, also known as the DAC, is used to convert the digital signal generated in our computers to analog forms. DACs are mostly used to generate sound and music. These lessons and the next lessons focus on information management. We learn about what information we need to keep and what information we cannot afford to lose. And these guidelines will help us understand benefits of concepts like sampling theorem, ADC resolution, analog filters, and some other very important concepts. So let's say we have an analog signal we wish to digitize, a change in voltage with time. Before this signal can be viewed and processed by a computer, it first needs to go through the analog to digital converter. The ADC also known as the analog to digital converter, has two main modules, the sample and hold module and the quantizer. The sample and hold module keeps the voltage constant while conversion is taking place. The sample and hold module is allowed to change only at periodic intervals, at which time it is made identical to the instantaneous value of the input signal. This means changes in the input signal that occur between these sampling times are completely ignored. By doing this, the sampling process converts the independent variable, which is time, in this example, from its continuous form to its discrete form. The digitization process performed by the digitizer converts the dependent variable, which is voltage, in this example, from its continuous form to its discrete form. So, in summary, the sample and hold is used to convert the independent variable from continuous to discrete, and the quantizer converts the dependent variable from continuous to discrete. And that's all there is to it, and leave your questions below. I'll see you in the next lesson. Hello fellas, welcome back. So when we say proper sampling, we simply mean the ability to reconstruct the exact analog signal from the samples. The sampling theorem, also known as the Nyquist theorem, dictates that a continuous signal can be properly sampled only if it does not contain frequency components above half of the sampling rate. In other words, our sampling frequency must be greater than or equal to 2 times the maximum frequency component in the signal we are sampling. For instance, if we choose a sampling rate of 2000 samples per second, this requires the analog signal to be composed of frequencies below 1000 cycles per second. If frequencies above this limit are present in the signal, they will be aliased. Aliasing occurs when a sinusoid assumes another frequency that is not its own, just like a person assumes an alias name. Now let's take a look at what a normal DSP system would look like in order to meet the requirement dictated by the sampling theorem. We begin with an analog signal. Commonly, before the analog signal reaches the ADC, we may have to process the signal with an analog low-pass filter to remove all frequencies above the Nyquist frequency. This analog low-pass filter is often known as the anti-aliasing filter, and the Nyquist frequency is defined as half the sampling rate. Once this is done, the signal can be sent to the ADC. The digital signal produced by the ADC is fed into the digital signal processing algorithm to perform spectral analysis, or the specific function the algorithm was designed to do. If we wish to send out the signal that we have processed in an analog form, like audio, we send a digitized output from the DSP algorithm to the digital to analog converter, or the DAC. The DAC processes the signal through the reconstruction filter before the signal is finally sent out and received at its destination. So that's all there is to it. If you have any questions, send me a message or leave your question below, and I'll see you in the next lesson. Hello fellas, welcome back. So, 3 types of analog filters are often used in DSP systems. These are the Bessel filter, the Chebyshev filter, and the Butterworth filter. Each of these filters is designed to optimize different performance parameters. Before we get to these filters, let's take a look at the building blocks of analog filters in general. Let's start with the RC passive low pass filter. The abbreviation RC implies resistor capacitor, and passive means it's got no active component. From basic electronics, we classify resistors, capacitors, inductors, diodes, and transformers as passive components, while devices like transistors and ICs, etc. are classified as active components. The RC low-pass filter is made of capacitors and resistors only, and it is a low-pass filter. Why? Because it allows us to choose a frequency below which signals with frequency component should be allowed to pass. For instance, let's say we pass a signal made of high frequency component and low frequency component through our low-pass filter. This one over here. At the output of the low-pass filter, only the low-frequency component will exist, like this. The most obvious question becomes, how do we make it reject the high-frequency component and pass the low-frequency component?
And the answer is we set the cutoff frequency. And we do this by selecting resistor and capacitor values that will give us the desired cutoff frequency. The cutoff frequency can be calculated with this equation here, 1 over 2 pi RC, where R and C represents the resistor and capacitor values respectively. This calculation can easily be done by hand, by deciding your cutoff frequency and then calculating backwards for your resistor and capacitor values. However, due to the usefulness and popularity of signals and systems, tools such as websites and simulators have been designed to help us make these calculations and even more complex ones. So the website I use is this one over here, and you can find it by going to Google and searching RC filter design tool. And then you see this first link. The website is sim.okawa-design-denshi.jp. It's a Japanese website. It's very simplified and it produces very good results. So let's click and see. Okay, it brings us here, but you would want to come over here to filter tools to get the filter you're looking for. So over here you can select the type of filter you want, and the one we've just spoken about in our lecture is this one here, the RC low pass filter. So I'll just click here. So when I click it brings me to this page, and I've got options here. If I want to calculate the transfer function for a low pass filter, given that I already have my resistor and capacitor values, I can use this side over here. But what is often more useful is you calculating the resistor and capacitor values you need, given that you already know your cutoff frequency. So let's say I'm designing a circuit and I'm trying to design a filter with a cutoff frequency of 5 Hz. I can come to the side over here, calculate R and C values for the filter at a given frequency. So FC over here, I can just put 5 and the unit is Hertz. So once I put 5, I can just hit enter and then it will generate the resistor and capacitor values I need for my filter. I'll just hit enter. And as you can see, there's the generated result. It says, okay, you can use resistor of 330 ohms and a capacitor of 100 microfarad, and your cutoff frequency, although you said 5, it's 4.8 Hertz. So this is how much I can get with these values. So it's tried to get it as close as possible as the value I put in here. But if I'm not very satisfied, let's say I don't have this resistor or capacitor value in my toolbox, or I really want to get a cutoff frequency as close to 5 as possible, I can come and change this here. This here is a standard that you change, which optimizes your resistor and capacitor value. It sort of compromises precision with giving you other options of resistor and capacitor values. So we've got E24, E12, E6, E96. I'll select E96 here and then just hit enter again. And with E96, now you can see it says, okay, I've rerun the simulation. If you use 316 ohm and 100 microfarad capacitor, you get a cutoff frequency of 5.036. This sounds like the cutoff frequency I want. And if you have these resistors, if you can get this, then that's perfect, you get this. So then you can just put in your cutoff frequency and play with the standards here and until you get the resistor and capacitor values that you have that you can use. So this is a very useful tool. There are other tools out there. Those are more complex and much more convoluted. This is very simplified and it's straightforward and it's a simple website really. So it provides the graphs as well. It provides the board diagram. It provides the impulse and step response graphs, which we shall take a look at in this course. But we can come here and examine the graphs, and you can play with this website, explore it, and see how useful it is to you. If you have any questions, of course, let me know. So let's move on. Hello, fellas. Welcome back. So to make a high-pass filter, we simply swap the positions of the resistor and the capacitor of the low-pass filter. A high-pass filter blocks the frequency components below the cutoff frequency and allows frequency components above the cutoff frequency to pass. So if we put a signal with a high frequency component and a low frequency component through the high pass filter, we will get the high frequency component at the output. The formula for calculating the cutoff frequency is the same as
the one we use for the low-pass filter, 1 over 2 pi RC, where R and C represent the resistor and capacitor values, respectively. And also we can use the same website we use to calculate our cutoff frequency to calculate our high-pass cutoff frequency as well. So this is where we left off from the simulation website. So this is the design of a low-pass filter. To get a high-pass filter, I come to this tab here called Filters. Now when I click, I can come over here and select RC high-pass filter tools. And then the interface looks the same, everything looks the same. I come over here, I select my cutoff frequency like we did before. I'll still use a 5 Hz cutoff for the high-pass. And then it produces the same result. When I adjust this to 96, I should have the same values. I just click in here and hit enter. And as you can see, 316 ohm and 100 microfarad. And the cutoff is 5.036. But this time it's a high pass filter, not a low pass filter. This time the capacitor and resistor positions are swapped, meaning frequencies above this frequency would pass through the filter. Whereas in the low pass case, frequencies above this will be attenuated, it wouldn't go through the filter. So it's very straightforward. You can get a standard resistor like this and a capacitor of this size and simulate this circuit and see how it works. If you have any questions, you can send me a message, but it is very, very straightforward like this. So let's move on. So now that we understand how the RC high pass and low pass filters work, in the next lesson, we shall look at an improvement over these basic filters known as the Modified Sallen-Key filter. And I'll see you in the next lesson. Hello, welcome back. So this is the response of our RC passive low-pass filter. There is a passband, a transition region, and a stop band. Ideally, we want our filter to have just the passband and stop band. We want it to transition straight from the passband to the stop band. We want it to look like this. This idealized filter is what is known as the brick wall filter. To get as close to this performance as possible, we have to improve our standard RC filter. This brings us to the Modified Sallen-Key filter. This filter is made up of both active and passive components. The operational amplifier here is an active component. The complexity of a filter can be adjusted by selecting the number of poles and zeros. Poles and zeros are mathematical terms which we shall discuss in future lessons. But for now, I want you to keep in mind that the more poles in a filter, the more electronic component it requires, and the better its performance. The Modified Sallen-Key filter we have here is a 2-pole low-pass filter. As we shall see later, we can construct more poles by cascading this configuration here. The way to compute the values of the resistors and capacitors we require is to use selected K1 and K2 values. These values are documented for different configurations of the Sallen-Key. Once we have chosen the K1 and K2 values from the list of values, we can select R1 and C values randomly and then calculate for R and RF using these two equations. By cascading a number of modified Sallen-Key filters, we can construct any of the 3 most commonly used filters in DSP applications: the Bessel, the Chebyshev, and the Butterworth filter. For example, by cascading 3 modified Sallen-Key filters, we get a 6-pole Bessel filter, like displayed over here. This is the first stage, the second stage, and the third stage. So, we shall see the performance of the 3 analog filters used in DSP in the next lesson. Don't forget to send me a message if you have any questions, and I'll see you in the next lesson. Hello fellas, welcome back. 3 types of analog filters are commonly used: the Bessel, the Chebyshev, and the Butterworth. Each of these is designed to optimize different performance parameters. And as we mentioned earlier, any of these filters can be constructed by cascading the Sallen-Key filter we spoke about in the previous lesson, or in fact, just by selecting specific K1 and K2 values for the Sallen-Key equations. For instance, if we have a single stage Sallen-Key filter like this circuit above here, and we select K1 as 0.1251 and K2 as 0.268, we shall have a Bessel filter. This works because K1 and K2 values shall decide the values of the resistors R and RF. In the same way, we can create a two-stage Butterworth filter by cascading two Sallen-Key filters and then choosing the K1 and K2 values of the first stage and the second stage. If we choose a K1 value of 0.1592 and a K2 value of 1.235 for the second stage, and a K1 value of 0.1592 and a K2 value of 0.152 for the first stage, we can create our two-stage Butterworth filter. With this table and the circuits above, one should be able to create any form of Bessel, Butterworth, or Chebyshev filter. So this is it. And also you should note that a single stage gives us two poles, so the standard single stage Sallen-Key filter, like this circuit over here, has two poles. So I'll just explain this table a bit. This table gives the number of poles here, and then the Bessel K1 and K2 values, the Butterworth K1 and K2 values, the Chebyshev K1 and K2 values. If you have just one stage, you have two poles. If you have two stages, you have four poles. If you have three stages, 6 poles. 4 stages, 8 poles. I think you get the progression here. So let's say you have a two-stage. You're creating a two-stage filter. Therefore, a 4-pole filter. You're creating two stages. If you have to use for the first stage these values here, 0.1111 for K1 and 0.084 for K2 for the first stage, and then the second stage you use 0.0991 for K1 and then 0.759 for K2, then you've created a Bessel filter. In the same way, if you don't use these K1 and K2 values and use these K1 and K2 values for your first and second stage, you create a Butterworth filter, just keeping the circuit the same, just using different K1 and K2 values. But the circuit is the same, exactly the same. In the same way, if you use these values, then you have your two-stage Chebyshev filter. And as I mentioned, this works because the K1 and K2 values will decide the values of the resistors R and RF. In the next lesson, we shall compare the performance of the Bessel, the Chebyshev, and the Butterworth filter. So like I always say, if you have any questions, leave it in the question section or send me a message, and I'll see you in the next lesson. Hello, welcome back. The first performance we want to explore is the cutoff frequency sharpness. As we mentioned earlier, a low-pass filter is designed to block all frequencies above the cutoff frequency. This is known as the stop band, while passing all frequencies below the cutoff frequency. This we call the pass band. We define the roll-off as the drop in amplitude. Let's begin with comparing the frequency response of the Chebyshev, Butterworth, and Bessel filter. These three graphs represent the Chebyshev, Butterworth, and Bessel filter, all with a 1 Hz cutoff frequency. In terms of frequency response, we can see the Chebyshev is the best. Remember, the ideal frequency response is the brick wall look. In these three filters, the Chebyshev is the closest to the brick wall look, followed by the Butterworth filter. The Bessel filter has the worst frequency response, as we can see from its gradual roll-off. When comparing frequency response, we want the filter with the fastest roll-off, meaning the one with the quickest drop in amplitude. Next, we shall compare our three filters in terms of their step response. We define the step response as a filter's response to rapid change in input value. This is the step response of the same three filters whose frequency response we just examined. We can see that the Butterworth and the Chebyshev filters are characterized by overshoots and ringings. In comparison, the Bessel has a smooth, perfect step response. To explain further, this graph here means rapid changes in input will take, in fact, more than 4 seconds to settle to be perfectly and truly represented in the output of the Chebyshev filter. In the Butterworth filter, this will take about 3 seconds. Meanwhile, in the Bessel filter, it will take less than a second. In conclusion, although the Bessel filter has the worst frequency response, it makes up for it by having the best step response. Based on your application, you can decide whether you want the best step response or the best frequency response, and this will help you choose between the Bessel or the Butterworth or the Chebyshev. As you can see, the Chebyshev has the best frequency response, the Bessel has the best step response, the Butterworth is in between the two. So this is all there is to it, and if you have any questions, leave it below or send me a message, and I'll see you in the next lesson. Hello, welcome back. So before we conclude this section on analog filters, let's talk a bit about information encoding. There are many ways for information to be encoded in an analog waveform. The two most common ways are the time domain encoding and the frequency domain encoding. In frequency domain encoding, the information is contained in the sinusoidal waves that combine to form the signal. An excellent example of a frequency domain encoded signal is audio. When we hear sound, the perceived sound depends on the frequencies present and not on the particular shape of the waveform. Consequently, digitization of these signals usually involves using an anti-aliasing filter, such as a filter with a very sharp roll-off like the Chebyshev or the Butterworth filter. Although these filters have a bad step response, the encoded information is not affected by the step response because these filters have excellent frequency response. Time domain encoding uses the shape of the waveform to store information, and a good example of this is the ECG or EKG acquired by the doctor. The shape of the ECG signal provides the information the doctor is looking for. So this is it, and I'll see you in the next lesson. Hello, welcome back. So in this section, we're going to start by talking about linear systems, and then at the end, we dive into the concept of superposition. Most DSP techniques involves a method known as superposition. This involves breaking the signal into simple components, processing each component separately, and then adding up the result of each processed component. Superposition can only be used with linear systems. So before we learn the superposition technique, we must first get familiar with linear systems. Earlier, we described a signal as how one parameter changes with respect to another. A system, on the other hand, is any process that produces an output signal in response to an input. We name continuous signals using parentheses and lowercase alphabets like this: x of t, y of t. When we name discrete signals, we use lowercase alphabet and square brackets like this: x of t, y of t. When we often talk about signals, by default we referring to them in the time domain. When we talk of frequency domain signals, we shall use uppercase alphabet. We shall see this later. Now let's look at what we mean when we say a system is linear. Mathematically, a system is called linear if it possesses two properties. The first property is homogeneity, and the second property is additivity. By proving that a system has homogeneity and additivity, we have successfully verified the system is linear. In signal processing, we can add a third property to these two. The third property is known as shift invariance. These three properties form the mathematics of how linear system theory is used in DSP. We shall elaborate further on these properties throughout this section. A system is said to be homogeneous if an amplitude change in the input results in an identical amplitude change in the output. In other words, if x of n results in y of n, then kx of n should result in ky of n for any signal x of n and any constant k, of course. Think of a simple resistor. If the input to the system is the voltage across the resistor, say V of t, and the output from the system is the current through the resistor, I of t, we can easily call the system homogeneous because we know that if we increase or decrease the voltage, there will be a corresponding increase or decrease in current, as is shown by the Ohm's law. So this is all there is about homogeneity. In the next lesson, we shall look at additivity. I shall see you in the next lesson. A system is said to be additive if added signals pass through it without interaction. What this means is, if x1 of n results in y1 of n, and x2 of n results in y2 of n, then x1 of n plus x2 of n should result in y1 of n plus y2 of n. It's as simple as this. This is what additivity means. So I'll see you in the next lesson as we talk about the shift invariance property. Hello, welcome back. So a system is said to be shift invariant if a shift in the input signal causes an identical shift in the output signal. In other words, if x of n produces y of n, then x of n plus s must produce y of n plus s. This is all there is to shift invariance. Apart from these three properties, homogeneity, additivity, and shift invariance, you may also come across sinusoidal fidelity as another property of a linear system in DSP. In fact, sinusoidal fidelity is properly applied more practically. It means if the input of a linear system is a sine wave or a sinusoidal wave, the output must be a sinusoidal wave and at exactly the same frequency as the input. So practically you can just test the linearity of a system by passing a sinusoidal wave through the system to see if the output produces a sinusoidal wave of the same frequency. So that's all there is, and I shall see you in the next lesson. Hello fellas, welcome back. So in DSP, the only way signals can be combined is by multiplying the signals by constants. This is known as scaling. After scaling, addition is performed. This is the only way signals can be combined. For instance, we cannot just multiply two signals to form a third signal. The process of combining signals through scaling and addition is known as synthesis. Decomposition is the opposite of synthesis, and it involves breaking signals into additive components. The overall method involving understanding how signals and systems can be analyzed is what is known as superposition. As mentioned earlier, in synthesis, two or more signals are added to form another signal. Decomposition breaks one signal into two or more additive parts. The property of decomposition dictates that any signal such as x of n can be decomposed into a group of additive components x0 of n, x1 of n, x2 of n. And when these additive components x0 of n, x1 of n, x2 of n are synthesized, we can get x of n again. When we take x of n and decompose it into x0 of n, x1 of n, x2 of n, and pass these decomposed components through a linear system, they in turn produce y0 of n, y1 of n, y2 of n. And when y0 of n, y1 of n, and y2 of n get synthesized, we get y of n back. So this is the process of decomposition and synthesis. It's very straightforward. The goal of decomposition is to replace the complicated signal with several easy ones. There are two main ways to decompose a signal in DSP. These are the impulse decomposition and the Fourier decomposition. We shall take a brief look at these decompositions and talk more about them in future sections. We shall also take a look at the step decomposition. So I'll see you in the next lesson. Hello fellas, welcome back. So impulse decomposition breaks an n samples signal into n component signals. Each component contains one point from the original signal, with the remainder point set to 0. In DSP, when we have a single non-zero point with all other points set to 0, we call this an impulse. As we can see over here, x of n has a number of samples. We can try counting them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. So the impulse decomposition takes each sample and then creates an entire signal with each sample. This one is taken, a signal is created. This one, a signal is created. This one, a signal is created. Each sample is taken to create an entire signal, and then the signal created from each sample has the same number of samples as x of n. Impulse decomposition allows the signals to be examined one sample at a time. Also, signals are characterized by how they respond to impulses. By knowing how a system responds to an impulse, the system's output can be calculated for any given input. In fact, this is how convolution works. We shall take a look at convolution in the next section. So as you can see in this example presented here, sample 1 is taken, and sample 1 maintains its amplitude and all other samples are set to 0. And then when we come over here, sample 2 is taken, and sample 2 here, it's sample 2, all other samples set to 0. When we come over here, sample 3, this is sample number 3. 1, 2, 3. Sample number 3, as you can see, is exactly the same amplitude is taken, and then all other samples are set to 0. And then in the same way, sample number 27 is taken over here, and all other samples are set to 0. So this is impulse decomposition. In the next lesson, we shall take a look at another form of decomposition known as the step decomposition. And I'll see you in the next lesson. Hello fellas, welcome back. So step decomposition is a bit similar to impulse decomposition in the sense that we still have n sample signal being broken into n component signals, each composed of n samples. But here, each component signal is said to be a step, meaning the first samples have a value of 0 while the last samples are some constant value. As we can see over here, the third component, which is x2, remember we're counting from 0. So x0 is the first component, x1 is the second component, x2 is the third component. So x2 here, x2 of n is composed of 0 for the point of sample 0, and then 0 for the point of sample 1, and then the point of sample x2, which is third, is this constant value here. In the same way, when we see here, x1, which is the second component, the constant value begins here, whereas the only component before x1 is x0, and therefore that is set to 0. Here there are two components before x2 and they are set to 0. And beginning from x2, everything is set to the constant value. In the same way, when we take x27 here, all components are set to 0 until we get to sample number 27, and then it all becomes a constant value. We'll see the importance of this method later. This is the way the step decomposition works. Step decomposition characterizes signals by the difference between samples and also characterizes the system by how they respond to change in the input signal. We shall leave the Fourier decomposition for the section on Fourier transform, and we've got about 2 entire sections dedicated to that. So that's all there is to it, and I'll see you in the next lesson. Don't forget to leave your questions below or send me a message, yeah? Hello, welcome back. In this section, we are going to talk about one of the most important mathematical concepts in all of DSP, convolution. Convolution is a mathematical way of combining two signals to form a third signal. Using the impulse decomposition method we studied in the previous section, systems can be described by a signal called the impulse response. Convolution relates three important signals of interest: the input signal, the output signal, and the impulse response. In the previous section, we learned how a signal can be decomposed into a group of components called impulses, and we also gave a description of an impulse as a signal with all points equal to 0 except one non-zero point. In effect, impulse decomposition provides a way to analyze signals one sample at a time. We also described the concept of superposition, which comprises decomposition and synthesis. Furthermore, we mentioned the two most important decompositions in DSP are the Fourier decomposition and the impulse decomposition. When impulse decomposition is used in the process of combining two signals, the procedure can be described mathematically by an operation called convolution. Now, let's take a look at the relationship between the delta function and the impulse response. First and foremost, a delta function is a normalized impulse response. And what this means is, sample number 0 has a value of 1, while all other samples have a value of 0, as shown here in this graph. Because of this, a delta function is often called the unit impulse. Now, when a delta function is passed through a system, the signal that comes out of the system is known as the impulse response. A good way to remember this is to think of the other name of the delta function, which is the unit impulse. When the unit impulse is passed through a system, we get an impulse response. What does this mean? Well, if two systems are different in any way, they will have different impulse responses. We often denote the impulse response as h of n, and the delta function is denoted as delta of n using the Greek letter delta over here. Basically, any impulse can be represented as a shifted and scaled delta function. For instance, let's say we have a signal a of n, like this. A of n is composed of all zeros for every sample except sample number 8, which has the value of -3. We can say that A of n is exactly the same as a delta function shifted to the right by 8 samples and then multiplied by -3. So if we have a system with an impulse response as input, such as -3 delta of n minus 8, we can find the system's output by using the properties of homogeneity and shift invariance we studied. This impulse input will give us an output of -3h of n minus 8. In effect, if you have any system's impulse response, you can immediately know how it will react to any other impulse. So this is all there is to it, and don't forget to send me a message if you have any questions. We'll be applying this in practical code, so don't worry if it's not very clear here, but you can send me a message if you need more explanation or if you have any questions, and I'll see you in the next lesson. Hello guys, welcome back. Let's begin this lesson by summarizing how a signal derives output signal from input signal. First, the input signal is decomposed into a set of impulses, each of which is a scaled and shifted delta function. Next, each impulse output is a scaled and shifted version of the impulse response. Remember, the impulse response is the output a signal produces when a delta function is passed through the system. So if the input signal is decomposed into scaled and shifted delta functions, known as impulses, then the output from each impulse will be a scaled and shifted version of the impulse response. Finally, the overall signal is found by adding the scaled and shifted impulse responses together. This is very powerful. This means if we know the system's impulse response, then we can calculate what the output will be for any possible given input signal. The impulse response goes by different names in DSP. If the system under consideration is a filter, the impulse response is known as the filter kernel, or the convolution kernel, or just the kernel. Although in image processing, the impulse response is called the point spread function. Convolution is just a mathematical operation like any other mathematical operation. Just like how multiplication takes 2 numbers and produces a third, convolution takes 2 signals and produces a third signal. Let's see what I mean. Let's say we have an input signal x of n, which enters a linear system with an impulse response h of n to produce the output y of n. We say that the input signal x of n convolved with the impulse response h of n produces y of n. In equation form, we write this like this. This star here is the convolution operator. We say x of n star h of n equals y of n. For example, if we have an input signal comprising a few cycles of sine waves and a slow-moving ramp, we can separate the sine waves from the ramp by using a properly selected impulse response. In fact, this particular illustration represents a low-pass filter. Later on in this course, we shall learn how to develop algorithms to perform functions such as this. In DSP, we can analyze convolution in 2 separate ways. The first way involves analyzing how each sample in the input signal contributes to many points in the output signal. The second method involves analyzing convolution from the perspective of the output signal, and we can do this by examining how each sample in the output signal has received information from many points in the input signal. As we shall see later, the first way provides us with the conceptual framework for understanding convolution, whereas the second method describes the mathematics involved in convolution. So let's take a look at this example. Let's say we have an input signal x of n, and x of n is a 9-point input signal from 0 through 8. If you count the number of tiny squares, you get 9. Now let's say we pass x of n through a system with a 4-point impulse response h of n to produce y of n, which is the output signal. Now let's decompose y of n and see what we have. As we mentioned earlier, each of these 9 points or samples will contribute a scaled and shifted version of the impulse response to the output signal. Let's see the contribution of each point. Let's start with sample 0 over here. Sample 0 is at index 0, x of 0, as we can see. The value of the sample 0 is 0. When the signal is decomposed, this turns into the impulse represented as 0 times delta of n minus 0. After passing through the system, the resulting output component will be 0 times h of n minus 0. And of course, the resulting output component is 0 as shown in the graph. The squares show the data points that come from the shifted and scaled impulse response, and the diamonds for the added zeros. Now let's examine x of 4. The sample is at index number 4 and has a value of 1.4. When the signal is decomposed, this turns into the impulse represented as 1.4 times delta of n minus 4. After passing through the system, the resulting output component will be 1.4 times h of n minus 4. If you look carefully, you will realize that this is the impulse response h of n multiplied by 1.4 and shifted 4 samples to the right. As you can see, this is the impulse response h of n. Over here, it starts from 0 and then it goes this way. If you come over here, you see that it's shifted 4 times. It's shifted here 1, 2, 3, 4. It begins over here and then it goes this way, multiplied by 1.4. So it's a bit higher. It's a bit higher, vertically higher this way. I know you get what I mean. This is the impulse response over here. It's shifted 4 times because of this. Shifted 4 times, and it's just a tiny bit higher. It's 0.4 times higher than over here. So if you look carefully, you will realize that indeed this is the impulse response h of n multiplied by 1.4 and then shifted 4 samples to the right. Zeros have been added at samples 0 through 3 and samples 8 through 11 to act as just placeholders to improve clarity. In fact, let's examine one more. Let's look at x of 8. From the input signal, we can see that x of 8 has the value minus 0.5 over here, x of 8. From the decomposition, we can see that x of 8 results in an impulse response that has been shifted to the right by 8 points and multiplied by minus 0.5. Zeros have been added at 0 through 7 for clarity. In this example, x of n is a 9-point input signal and h of n is a 4-point impulse response. In the next example, we are going to swap the positions of x of n and h of n. We are going to use the same waveforms, only this time the 4-point signal shall be used as the input signal and the 9-point signal shall be used as the impulse response. So now we have x of n, a 4-point input signal passing through h of n, a 9-point impulse response to produce y of n, the output signal. As we can see, y of n remains the same. If we decompose output signal y of n, we see that the 4 points in the input signal x of n produces 4 shifted and scaled versions of the 9-point impulse response. And as we can see from the comparison with the previous one, the output signal y of n is the same. In fact, we have just proven that convolution is commutative. So that's all there is to it. I may have moved a bit too fast. If you have any questions or if you need more explanation on any of the material, please leave your question below or send me a message and I'll respond very promptly. And I shall see you in the next lesson. Let's examine how a single point in the output signal is influenced by several points from the input. Let's say we have an input signal x of n, which is convolved with an impulse response h of n to produce an output y of n. What we are going to do is examine point number 6 of the output signal. First of all, let's decompose the output signal. When we decompose the output signal, this is what we get. We get 9 separate plots because, as we mentioned earlier, the output signal is merely a synthesized version of the scaled and shifted versions of the impulse response. Since our input signal has 9 samples, there are going to be 9 scaled and shifted versions of the impulse response. When these 9 scaled and shifted versions of the impulse response are synthesized, we get the output signal, y of n. In the same way, when we decompose y of n, we get the 9 scaled and shifted impulse responses. I hope that's not very confusing. Right, moving on. Now, let's look closer at the 9 components and identify which can affect y of 6. And to do this, we simply find which of these 9 signals contains a non-zero sample at the 6th position, at position number 6. As we can see, this first component here has 0 at the position number 6. So that's the second component as well as the third component. They all have 0 at position 6. But the fourth component has a value of around minus 0.2 at position 6. And the fifth component also has a non-zero value at 0.6. And the sixth and the component number 6 also has a non-zero value as well as component number 7, which isn't shown here. All of these components marked in red have non-zero values at position number 6. So we can determine y of 6 as follows by selecting those components with non-zero values at position number 6 and then performing this operation. So this is it. I've expanded it here. Over here, this first term corresponds to this one here, x of 3. So x of 3 multiplied by hn minus 3 for this, and then for x of 4, the second term here, x of 4 multiplied by h of n minus 4, and then for 5 this, and then we know n equals 6, right? So we just plug in 6 over here, and then it becomes x of 3 multiplied by h of 6 minus 3, and then over here h of 6 minus 4, h of 6 minus 5, h of 6 minus 6, and then we compute this. This means 4 samples from the input signal are multiplied by 4 samples in the impulse response, and the products are added. This brings us to the idea of the convolution sum, the standard equation of convolution. If x of n is an n-point input signal running from 0 to n minus 1, and h of n is an m-point signal running from 0 to m minus 1, the convolution of x of n and h of n is an n plus m minus 1 point signal running from 0 to n plus m minus 2. You don't need to worry about all of that. It is summarized in this very elegant equation. This is called the convolution sum, and it allows each point in the output signal to be calculated independent of all other points in the input signal. We shall build the algorithm to implement the convolution sum in our development environment. So that's all there is to it, and if you have any questions, please leave it below or send me a message, and I'll see you in the next lesson. Hello fellas, welcome back. In the first perspective of the convolution analysis, we saw how each input signal affects many samples in the output signal. In this second viewpoint, we shall reverse this by examining each sample in the output signal and finding the contributing point from the input. Let's examine how a single point in the output signal is influenced by several points from the input. Let's say we have an input signal x of n, which is convolved with an impulse response h of n to produce an output y of n. What we are going to do is examine point number 6 of the output signal. First of all, let's decompose the output signal. When we decompose the output signal, this is what we get. We get 9 separate plots because, as we mentioned earlier, the output signal is merely a synthesized version of the scaled and shifted versions of the impulse response. Since our input signal has 9 samples, there are going to be 9 scaled and shifted versions of the impulse response. When these 9 scaled and shifted versions of the impulse response are synthesized, we get the output signal, y of n. In the same way, when we decompose y of n, we get the 9 scaled and shifted impulse responses. I hope that's not very confusing. Right, moving on. Now let's look closer at the 9 components and identify which can affect y of 6. And to do this, we simply find which of these 9 signals contains a non-zero sample at the 6th position, at position number 6. As we can see, this first component here has 0 at the position number 6. So that's the second component as well as the third component. They all have 0 at position 6. But the fourth component has a value of around minus 0.2 at position 6. And the fifth component also has a non-zero value at 0.6. And the sixth and the component number 6 also has a non-zero value as well as component number 7, which isn't shown here. All of these components marked in red have non-zero values at position number 6. So we can determine y of 6 as follows by selecting those components with non-zero values at position number 6 and then performing this operation. So this is it. I've expanded it here. Over here, this first term corresponds to this one here, x of 3. So x of 3 multiplied by hn minus 3 for this, and then for x of 4, the second term here, x of 4 multiplied by h of n minus 4, and then for 5 this, and then we know n equals 6, right? So we just plug in 6 over here, and then it becomes x of 3 multiplied by h of 6 minus 3, and then over here h of 6 minus 4, h of 6 minus 5, h of 6 minus 6, and then we compute this. This means 4 samples from the input signal are multiplied by 4 samples in the impulse response, and the products are added. This brings us to the idea of the convolution sum, the standard equation of convolution. If x of n is an n-point input signal running from 0 to n minus 1, and h of n is an m-point signal running from 0 to m minus 1, the convolution of x of n and h of n is an n plus m minus 1 point signal running from 0 to n plus m minus 2. You don't need to worry about all of that. It is summarized in this very elegant equation. This is called the convolution sum, and it allows each point in the output signal to be calculated independent of all other points in the input signal. We shall build the algorithm to implement the convolution sum in our development environment. So that's all there is to it, and if you have any questions, please leave it below or send me a message, and I'll see you in the next lesson.
Hello fellas, welcome back. As we have seen in this section, a linear system's characteristics are completely specified by the system's impulse response. For example, digital filters and other signal detection systems are created by designing an appropriate impulse response. In this lesson, we're going to examine some of the properties of convolution. Let's begin by examining the identity property of convolution. As we said, the most basic impulse response is the delta function. Convolving any signal with a delta function results in exactly the same signal. This is expressed mathematically like this: x of n convolved with delta of n equals x of n. This property makes delta function the identity of convolution, just like the way 0 is the identity of addition and 1 is the identity of multiplication. Let's expand on this further. If a delta function is increased or decreased, our system becomes an amplifier or an attenuator respectively. To express this mathematically, x of n convolved with k delta of n equals kx of n. If k is greater than 1, we get an amplifier. If k is less than 1, we get an attenuator. Also, if the delta function is shifted, the output is shifted. Mathematically, this is expressed as this: x of n convolved with delta of n plus s equals x of n plus s.
Hello fellas, welcome back. So in this lesson, we're going to see how to perform convolution in Matlab. So this is my Matlab I've opened. I've cleared everything over here, and I've cleared my command window as well.
So what we're going to do is we're going to generate a number of signals. We're going to generate a signal and then mix it with some noise. And what I mean by this is we're going to generate a 1 Hertz signal and then generate another signal of a frequency of 20 Hertz and combine these two signals. Then we're going to design an impulse response which will be in the form of a low pass filter with a specific frequency response, so that when we convolve the impulse response with our mixed up signal, we get an output signal. So let's start by generating our first signal. Let's say F1 here, meaning frequency 1 equals 20. We want a 20 Hertz signal, and we want a sampling frequency TS, or a sampling period of 1/100, meaning sampling frequency of 100 Hertz. And we can make the signal length 3 seconds, capital T equals 3. And then we can say T, small t, equals 0 to capital T with interval of TS like this. We can put a semicolon here. And we can call this signal 1. And we can call this, let's give it a bit more descriptive name. I'll call it signal 20_20 Hertz, right? Because we're going to have something very long and it's going to look confusing if it's not descriptive. So we can call it signal_20 Hertz equals, to create the signal, we say sine into bracket 2 times pi times frequency, which is F1, and then times T here, then semicolon, and then let's plot to see our signal. We can say plot signal_20 Hertz, and this is what we have. It's a 20 Hertz signal, right? So let's create the other signal. We can come down here and say F2 equals 1, meaning we want a 1 Hertz signal. And now we can use the same equation, but this time we pass F2 over here. So I can say signal_1 Hertz equals sine into bracket 2 times pi times F2 times T like this. And we'll put a semicolon here. Let's plot signal 1 Hertz and see. Plot into bracket signal 1 Hertz, put a semicolon, and this is what we have. Very simple low frequency signal. So we're going to combine this 20 Hertz signal and 1 Hertz signal. So we can say signal_20 Hertz _ 1 Hertz. This is just to give a descriptive name, meaning the combination of 20 Hertz and 1 Hertz equals signal_20 Hertz plus signal_1 Hertz like this. So we add the two vectors and then we get a combined signal. So we hit enter. So now let's plot signal 20 Hertz, 1 Hertz. So plot into bracket signal_20 Hertz _1 Hertz like this. And let's see, this is what it looks like. Right. So this is our final signal. This signal has a 20 Hertz high frequency component and a 1 Hertz component within this. So what we're going to do next is design a filter or design an impulse response. And as we go on, when we get to the part on filter design, you realize that the same method that we're using here in the convolution lesson will be used to design various frequency response filters. So to design a filter in Matlab, there is a tool known as the FDA tool which we can use. So to go to the FDA tool, we can just say FDA tool, type it here like this, hit enter. So it's given a warning. It says FDA tool is going to be removed and filter designer is going to be used instead. So later on, if you type FDA tool and you receive an error, you can just type filter designer. Right. So yeah, I minimized FDA tool. Here it is. This is what it looks like. So over here, we can design different responses of a filter, and then we can select the various parameters. So what we want is a low pass filter, and we want FIR. You would understand the difference between FIR and IIR later when you get to the section on filter design. So just come to FIR. Over here, we just need an impulse response. FIR, so you select least squares. Select this one here. And here we can decide the pass band and the stop band of our filter. We can say F pass equals 1, F stop, we can say F stop equals 6. So 1 Hz pass band, 6 Hz stop band. And we can say the filter order, let's give it a number like 39. We can make the Fs over here 100 equal to the Fs of our signal, and then we click here to design. So this is our filter. This is the magnitude response of the filter. So what's going to happen is, because our signal has 20 Hz and 1 Hz component, the 1 Hz component is in the pass band. So it's going to go through the filter perfectly, but the 20 Hz component is going to be massively attenuated, and we expect the output signal not to contain 20 Hz. So this is what the magnitude looks like. We can view other graphs here as well. This is the phase response, and this is the impulse response. This is what we're interested in. So this is the impulse response. Right. So if we plot the values generated by this filter, it's going to look like this. This is the impulse response. So we can export the filter kernel or the impulse response. You can call it either a filter kernel or impulse response, but in this section on convolution, we're calling it the impulse response. So we can export this by coming here, click export, and then you can decide to export it anywhere. We want to export to our workspace, and then we can give the variables a name. We can call it impulse response imp_response like this, and then we can click here to export. And as you can see, it's appeared here. So once that is done, we can close our FDA tool. We don't need to save it. No, like this. So we can plot the impulse response. Plot imp response. And this is what we have, just like we saw in the FDA tool. So this is the impulse response. We're going to convolve this waveform with the 20 Hz, 1 Hz signal we saw earlier. So let's do that now. So all we need to do is use the conv function. We can say output signal here equals conv, and conv is for convolution. And then we pass the two waveforms we want to convolve. So we want to convolve the signal underscore 20 Hz underscore 1 Hz, comma, the second argument is the second signal, which is imp underscore response. So we have the solution. We can plot the output signal, but rather than plot just this signal, let's plot all three signals and see what it looks like. We're going to use something known as subplot. So to do that, we can just say subplot, and then subplot takes 3 arguments. The first argument is the number of rows you want. So you see how we've been plotting just one graph per window. Now we want to plot 3 graphs. So I'm going to say I want 3 rows. And the second argument is the number of columns. We want just 1 column. And this one here says which position of the rows. We have 3 rows. So I'm saying 3 rows, 1 column, position 1. It brings me here. So this is it. This is row 1 will be row 1 is here, row 2 is going to be here, row 3 is going to be here, but it's just 1 column, and this is position 1. Hence we are at the top here. Right. So once that is done, I can first plot the input signal. So I'll say plot signal underscore 20 hertz underscore 1 hertz. And as you can see, it's appeared here, and we can add a title to it. We can call this, we use the title function, title noisy. We can say noisy, you can give it whatever title you want. I'm just going to say noisy input signal, and I'll put a semicolon here. And then next, let's plot the impulse response. So to plot the impulse response, I have to change the subplot to select column number 2, to select position number 2. We still have, so this is the dimension, row, number of rows we want, number of columns, and we just need to be changing this last argument here. This will select the various rows. So let's see what I mean. So we can say subplot, and then over here I'm going to say 3, 1, now row number 2, and what I want to do is plot impulse response. And as you can see, if you check here, the impulse response has appeared over here, and we can give it a title as well. Title impulse response, like this, and the title will appear. And we plot, finally, let's see the result, the output signal, the result generated by the convolution. So now we are going to say 3, 1, 3, that's the last row. So subplot 3, 1, 3. And what we want to do is plot output signal, output underscore signal, like this. And we have to give it a title. Output, you can say output from convolution, just to make it descriptive. Okay, hit enter. Now let's see. Okay, so to bring the plot forward, we don't always have to go and find a particular window. We can use the shg command. And this is what we have. Right, perfect. So this is our convolution demo. So we started with this input signal, and we created this input signal together. We took a 20 hertz signal and a 1 hertz signal, we combined them, and then we ended up with this very noisy signal. Then we went to the filter design tool, and then we created this impulse response, and this impulse response was specifically designed to be a low pass filter with a pass band of 1 hertz and a stop band of 5 hertz. When we convolve these two, this is the output signal that we get. So in effect, we've just designed a low pass filter. Imagine this is a signal you acquired from your sensor, and the signal is characterized by certain high frequency component. You can just import the signal to Matlab and design the impulse response given your own passband and stop band, and you'd get your output. You get your output signal like this, and you can use CSV write to write the output signal out of Matlab and export it to a file. So this is a very descriptive. In fact, let's add a heading to the entire window. To add a heading, we can say SUP title, meaning super title, and I'll just call the title of the entire window convolution, like this. Okay, subtitle, I think this has been removed from Matlab 2018. This works in the 2016 version. Super title was used in earlier versions to add a title on the top. If you have any questions at all, please do send me a message and I'll get back to you. And if you're finding this course useful in any way, please take some time off to leave a review, and it will be very much appreciated. So I'll see you in the next lesson.
Integration and differentiation are calculus operations used for continuous signals. Convolution can perform somewhat similar operations on discrete signals. The discrete operation of convolution, which is similar to the first derivative of continuous signals, is known as the first difference. The discrete operation of convolution, similar to the integral of a continuous signal, is called the running sum. Let's take a look at the first difference. The first difference is calculated like this. It says y of n equals x of n minus x of n minus 1. In other words, each sample in the output signal is equal to the difference between the two adjacent samples in the input signal. Applying the same approach, the running sum can be derived by y of n equals x of n plus y of n minus 1. For example, if y of 20 has already been calculated, y of 21 can be calculated with only a single addition. The importance of the first difference and the running sum will become very clear when we start designing our digital filters. To give you an idea, this type of equations are known as recursive and difference equations, and they play a significant role in designing infinite impulse response filters. Apart from these properties, convolution also obeys some basic math properties as well. For instance, convolution is commutative, meaning apart from these properties, convolution also obeys some basic math properties as well. For instance, convolution is commutative, meaning A of n convolved with B of n equals B of n convolved with A of n. Also, convolution is associative and distributive. So, there is this very short on the properties of convolutions. And if you have any questions, don't hesitate to leave them below or send me a message. And I shall see you in the next lesson.
Hello, welcome back. In this lesson, we shall see how to compute the running sum of a signal in Matlab. So what we're going to do first is import our last signal, the 20 Hz and 1 Hz. We have the signal where we combined 20 Hz and 1 Hz. We're going to use that same signal here. So it's over here in my project folder, so I'm just going to use the load function to import it. So I'm going to say input underscore signal equals load into bracket underscore 20 Hz underscore 1 Hz underscore sig.txt. That's the name of the file. Yeah, I have a typo. I put a comma here instead of a dot. Sorry about that. Right, so it's loaded. So the signal is loaded. Just to clear everything up, I'm just going to CLC to clear here, but I still have my input signal here. Right. So we can plot the input signal just for a reminder to see what it looks like. Plot input underscore signal. And this is what it looks like. It's got 1 Hz and 20 Hz in there. The running sum in Matlab is known as the cum sum, meaning cumulative sum. So we can compute the cumulative sum very easily by using the cum sum function. And we can read it, what it does by saying help cum sum like this. And it's going to provide a bit of help about this particular function. So it says compute the cumulative sum along the first non-singleton dimension. You don't need to worry about all of this, but if you want to read more about it, you can read it here. Right, so I'm just going to clean all of this again, CLC, and then I'm going to say output signal, output underscore signal. This is the vector that would contain the running sum result equals cum sum like this. And then I'm passing the argument input signal here. So I'll say input underscore signal like this and hit enter. So now let's plot the input signal and the output signal together to see the result. And we can use the subplot. So this time we need just 2 rows of plot because we have just 2 signals. So I'm going to say subplot 2 rows, 1 column, position number 1 over here. So then the next one is just going to be down here. And I'm going to plot input underscore signal, and I can plot this with a color red like this. And let's see, this is what it looks like. Great. So now we're going to plot below this the output from the running some computation. So I'm going to say subplot. Let's add a title first. Let's say title into brackets input signal, like this. And once that is done, we can plot the result by saying subplot row 2 column 1 position 2, and we can say plot output underscore signal, and we can make this green, use G over here, and we can give it a title, and we can just make the title descriptive by saying output signal from running some, just for your revision. I'll put a semicolon here, and I'll just type SHG to bring it in front. This is what it looks like. So the running sum is a very simple smoothing filter you can use. So imagine you just acquired this type of signal and it's so noisy and you don't know what to do. You can just pass it through a running sum, and this would clear up the signal a bit. And after this, it's easier to do things like peak detection in this signal compared to this one up here. So this is the nature of the running sum computation. So in the next lesson, we're going to see how to compute the first difference in Matlab. If you have any questions at all, just send me a message or leave in the questions area, and I shall see you in the next lesson. Hello, welcome back. So this is our last project where we computed the running sum. I'm just going to clean everything, and in this lesson, we're going to learn how to compute the first difference in Matlab. So I'm going to use CLC to clean everything, and I'm going to clean everything in the workspace as well and start from scratch. I'm going to say clear all over here like this, and I'm just going to CLC again just to make it look like this. And I'm going to import our signal again, the 20 Hertz, 1 Hertz signal. I'm going to come here and say input underscore signal equals load underscore 20 Hertz underscore 1 Hertz underscore sig.txt. And then we already know what the signal looks like, so we don't need to plot it. So Matlab has a function for computing the first difference as well, and this function is simply diff, D-I-F-F. And if you need help about the function, you can just type help diff, but we're not going to display the help document here. So what we're going to do is we say output signal, we store the computation result into this variable, this vector known as output signal. So I'll say output signal equals diff, and in here I'll say input underscore signal, I'll put a semicolon here. Now we have this. Now let's plot the input signal and the output signal, and let's see what we have. I'm going to use the subplot, and we have just two plots. So I'll say 2, 1, 1 here, and I'll come here and say plot input signal, input underscore signal, and I'll plot this in red, R for red, and I'll give it a title, input signal, and then I'll move to subplot 2, 1, 2, position 2 to plot the output signal. So I'll say subplot 2, 1, 2, and plot output underscore signal, and then comma green, G for green, like this. Yeah, I made a mistake in the typing, so I'm being corrected. Okay, I'll hit enter, and then once that is done, I'll just give it a title, and over here I'll give the name output from first difference and I can just use SHG to bring it in front. Yeah, we plotted this. We plotted the output on top of the input because we mistakenly used this. We used 1 position here. So let's just plot the input below. Yeah, just bear with me. So I'm going to say subplot 2 1 2, and over here I'll say plot input signal, and I'll give it a title input signal, and I'll bring it in front SHE. So this is what we have. So yeah, this is what we have. This is the input signal. This is the first difference, the results produced from the first difference. So this is the nature of the first difference computation. Later on, we shall see the usefulness of the first difference computation and the running sum. We'll get to the part on designing recursive filters. So that's all there is for this lesson. And if you have any questions at all, send me a message or leave it in the questions section. And I shall see you in the next lesson, yeah?
Fourier analysis is a family of mathematical techniques, all based on decomposing signals into sinusoids. As we shall see later, the one which we are most interested in is the discrete Fourier transform, DFT for short. This type of Fourier analysis is used with digitized signals. As we have mentioned earlier in this course, a signal can either be continuous or discrete, and it can also either be periodic or aperiodic. Combining these two parameters generates 4 categories of signal. We have periodic discrete signals, periodic continuous signals, aperiodic discrete signals, and aperiodic continuous signals. The type of Fourier transform used for analyzing periodic discrete signals is called a discrete Fourier transform, or DFT for short. The Fourier transform for analyzing periodic continuous signals is called the Fourier series. The one for analyzing aperiodic discrete signals is called the discrete time Fourier transform, or DTFT, and the Fourier transform for analyzing aperiodic continuous signals is simply called the Fourier transform. Don't give much thought into the names here. There is no particular order here. You just need to remember them the way they are. The Fourier decomposition involves decomposing a signal into sine and cosine waves. Just to give you an idea, a 16-point signal such as this one can be decomposed into sine waves and cosine waves using Fourier decomposition. I know it looks like 16-point signal being decomposed into 18 sinusoids. Don't worry much about it, but just to shed a bit of light over here, in more formal terms, the 16-point signals up here must be viewed as a single period of an infinitely long continuous signal. Therefore, each of the 18 sinusoids shown down here represents 16-point segment from an infinitely long sinusoid. All the 4 types of Fourier analysis can be computed using real numbers or using complex numbers only. In this section, we shall use just the real form. In the following sections, I shall show you how to use complex forms after we've given an introduction to complex numbers. Discrete Fourier transform, or DFT, changes an n-point input signal in the time domain into 2 groups of n over 2 plus 1 output point signals. One group of the output point signal contains amplitudes of the component cosine waves, and the other group of the output point signals contains amplitudes of the component sine waves. The time domain signal x of n consists of n points running from 0 through n-1. In the frequency domain, the DFT produces 2 signals, the real part signal written as REX and the imaginary part signal written as IMX. The real part signal represents the cosine wave amplitudes, and the imaginary part signal represents the sine wave amplitudes. I should also point out that this is still real DFT, not complex DFT. Although the frequency contains real part and imaginary part, I know it sounds a bit confusing, but it will get clearer once we introduce complex DFT. Given the time domain, the process of deriving the frequency domain is known as decomposition analysis for DFT or just DFT. Given the frequency domain, the process involved in deriving the time domain is known as either synthesis or inverse DFT. In DSP, we use the lowercase letters to represent the time domain signals, and we use the uppercase letters to represent the frequency domain signals, like we have here, capital X to represent frequency domain and small x to represent time domain signals. Now, let's take a look at three forms of representing the frequency domain information. Let's say we have a time domain signal with 128 point, meaning n equals 128, as plotted here from 0 to 127, and we perform the DFT. We shall get 65 point cosine wave and another 65 point sine wave. I know the sine wave over here shows 80, but don't worry about this. This waveform can also be extended to 64 and beyond, but this is the relevant bit, 0 to 64, 0 to 64. I just show this 8 here for uniformity for the other two ways of denoting the same waveform that we shall see very soon. So this means n point in the frequency domain corresponds to n over 2 plus 1 point cosine waves and n over 2 plus 1 point sine waves. There are three common ways of representing the frequency domain information. In this first version, the x-axis, which represents the frequency, is denoted as an array running from 0 through n over 2 plus 1. In the second mode of representation, the x-axis is denoted as a fraction of the sampling frequency running between 0 and half the sampling frequency. Since the sampling theorem dictates that the highest frequency component must be less than or equal to half the sampling frequency, we know that all of the useful frequency components can be represented between 0 and half the sampling frequency, which is 0.5 times f. The third mode of representation denotes the x parameters as a natural frequency running between 0 and pi. So these are really the three representations that we have. They are very common. You see them in books, you see them in other lectures. When you see any of these, you can just know that it's the same information represented. So this is all there is for this lesson. If you have any question, do leave it below or send me a message and I'll reply quite quickly. And I shall see you in the next lesson. Have a good one. Hello fellas, welcome back. The sine and the cosine waves in the DFT are often called the DFT basis functions. As we have seen, the output of the DFT represents amplitudes on the y-axis and frequencies on the x-axis. The basis functions are a set of sine and cosine waves with unity amplitudes. This is very important. In fact, this was the argument of Jean-Baptiste Fourier in 1807. What this means is, if we assign each amplitude of the frequency domain signal produced by DFT to a proper sine or cosine wave, in other words, basis functions, the result is a set of scaled sine and cosine waves that can be added to form the time domain signal, and we can generate the DFT basis function using these equations. Ck of I and Sk of I are the cosine and sine waves, each endpoint in length and running from I equals 0 to n minus 1. The parameter k determines the frequency of the wave. Ck is the cosine wave for the amplitude held at Rex, and Sk is the sine wave for the amplitudes held at Imx, the imaginary part. The key takeaway here is that the frequency parameter k is equal to the number of complete cycles that occur over the endpoint of the signal. Let's see what I mean. Let's say we have a 32-point DFT, meaning n equals 32. This 32-point DFT has n over 2 plus 1 cosine waves, in other words, 17 cosine waves, and n over 2 plus 1 sine waves, which also means 17 sine waves, running from 0 through 16. The actual waveform is not really relevant to this illustration. Let's examine some of those waves. S0 and C0 means K equals 0. These represent the sine and cosine waves of 0 frequency. In the same way, S1 and C1 means K equals 1 and represent the sine and cosine waves with 1 complete cycle. Then S2, C2 means 2 complete cycles, S3, C3 means 3 complete cycles. Likewise, S10 represents the sinusoids that complete 10 cycles, and S16 and C16 represent the sinusoids for highest frequencies in the basis function, which is 16 cycles in the endpoint signal. If you observe closely, you'll see that the discrete cosine wave alternating the value between 1 and -1. This is what is known as sampling a continuous sinusoid at the peaks. In contrast, the discrete sine waves contains all zeros resulting from sampling at zero crossing. This right here makes IMX of n/2 the same as IMX of 0, which are both always equal to 0 and not affecting the synthesis of the time domain signal. In summary, IMX of 0 and IMX of n/2 carry no information. N samples entering a DFT produces n+2 samples, and when these n+2 samples are synthesized back to time domain, n samples are produced. Let me know if there's something you do not understand, and I'll see you in the next lesson. Hello, welcome back. So the synthesis equation is also known as the inverse DFT, and it's written as follows. In this expression, x of I is the signal being synthesized with the index I running from 0 to n-1. Rex bar of k and Imx bar of k hold the amplitudes of cosine and sine waves respectively, with k running from 0 to n/2. Now I know that's the first time we have introduced x bar. Let's see what it means. As we mentioned earlier, the frequency domain signal is made of cosine wave and the sine wave. The cosine wave is the Re part, meaning Rex of k, and the sine wave is the imaginary part, meaning Imx of k. These are the frequency domain signals. Rex bar of k and Imx bar of k are the amplitudes needed for synthesis, and we can derive Rex bar of k and Imx bar of k from Rex of k and Imx of k. Let's see the relationship. We can find Rex bar of k by simply dividing Rex of k by n/2. In the same way, we can find Imx bar of k by simply dividing Imx of k over n/2, except in Rex bar of 0 and Imx bar of 0, where Rex bar of 0 is equal to Rex of k over n, and Imx bar of 0 equals Imx of k over n. As simple as this. From the synthesis equation, any endpoint signal x of I can be created by adding n/2 plus 1 cosine waves and n/2 plus 1 sine waves. The amplitudes of the cosine and sine waves are held in the arrays Imx bar of I and Rex bar of k. The synthesis equations multiplies these amplitudes by the basis functions to create a set of scaled sine and scaled cosine waves. Adding these scaled sine and cosine waves together produces the time domain signal x. We shall write code to demonstrate this. But before we do that, let's take a look at the synthesis process a bit more. Let's say we have to synthesize this time domain signal. In other words, we wish to get this time domain signal from the frequency domain. This time domain signal is an impulse at sample 0 with an amplitude of 32. This is what the real part of the frequency domain looks like. The imaginary part is not shown here. That's not very relevant. It's made up of all zeros. To find the time domain from the frequency domain, we have to use Rex of k to find Rex bar of k, and then use Rex bar of k, and then use Rex bar of k in our synthesis equation to find the synthesis. So this is very short. This is all there is to it. Don't hesitate to send me a message if there is something you do not understand, and I'll see you in the next lesson. Hello fellas, welcome to this lesson. So in the last practical lesson, we saw how to find the discrete Fourier transform of a signal in Matlab. And what we did was we took
we took a time domain signal and then passed it to the FFT function, and then we were able to get a frequency domain signal from that. In this lesson, what we're going to do is take the same time domain signal, pass it to the FFT function. When we get a frequency domain signal from that, we take that frequency domain signal and pass it to another function known as the IFFT function, meaning Inverse Fast Fourier Transform. And then let's see whether we get the same time domain signal back. And through this, we would compute the Inverse Fourier Transform. So let's get started. Let's import our signal here. I'll just CLC to clean. And I'm going to say input signal, input underscore signal equals load. And I'm going to say over here underscore 20 hertz underscore 1 hertz underscore sig.txt. And then what we want to do is find the frequency domain, and I'm going to say y equals FFT, and then we'll pass input signal here, input underscore signal. And once we found this, we don't need to plot the magnitude and the phase, so we can leave that out for now. So we have the frequency domain of we have the frequency domain stored in this vector here, this vector y. And actually, to make it more descriptive, I'm going to change the name of this y here to DFT output. So I'm going to say DFT output. I'm going to create a new vector, DFT underscore output equals FFT input signal, input underscore signal, like this. And let's just compute the magnitude and keep it for plotting sake. So I'll say DFT output underscore mag for magnitude equals ABS DFT underscore output, like this. So now to compute the inverse Fourier transform, we just need the content of this vector here that we call DFT output. Because when the frequency domain signal was generated, it was stored in this vector. So we can say IDFT underscore output equals IFFT. IFFT is the function for computing the inverse discrete Fourier transform. And then over here we pass DFT output, like this. So once we've done this, we can go ahead and plot the three signals. And by the three signals, I mean the input signal, the magnitude from the DFT, and then the output generated by the IDFT computation. So I can say subplot over here, subplot 3, 1, 1. Then we have this here. What I want to do is plot the input signal first, plot input underscore signal, and I'm going to plot this in, let me just plot this in red, or use R over here, and I'll give it a title, input signal. And then let's plot the magnitude of the frequency domain signal, which we saw in our previous practical lesson. So I'll just come down here and say subplot 3, 1, 2. And what we want to do is plot output underscore plot DFT output mag, DFT underscore output underscore mag. And we want to plot this in the color of, how about we choose a color such as yellow. I'll put yellow here. And then we can give it a title. We can call it frequency spectrum. Once that is done, we can plot the final one, which is what we're truly interested in the signal generated by the IDFT. So we can say subplot 313, and what we want to do is plot IDFT underscore output, and we can give this a color of green. So there's a typo. Good, I'm corrected. That's good. And then we can give it a title here. We can call this signal from IDFT, like this. And once that is done, we can use SHG to bring it in front. Okay, we don't have this plotted. Okay, we forgot to change the subplot. So it's plotted here and then put the wrong heading there. So let's just fix that. Right, bear with me, yeah? I'll just view it again, SHG. Currently we have the input signal here, but the heading is wrong. So I'm just going to set the heading. Then after that, I'm going to bring the subplot here and plot our output IDFT signal. So I'm going to set heading to input signal. And let's see what I mean. Okay, so we have input signal here. So now I'm going to say subplot 313, and then I'll come over here and plot what we need to plot. Subplot 313, and I can just say plot IDFT output with color green, and then I can give it a title, signal from IDFT, like this, and we can say SHG, and this is what we have. Indeed. Right, the yellow was probably a bad choice. We wouldn't use yellow again. So indeed, our IDFT was able to reproduce the time domain signal that we started with. We took this time domain signal, we passed it through the DFT algorithm, we got this frequency spectrum, and we took the frequency spectrum, we passed it through the IDFT algorithm, and we're able to generate the time domain signal from this. So that's all there is for this lesson, and if you have any questions at all, please do send me a message or leave in the questions area. And if you're finding the course useful, please leave your review. And I shall see you in the next lesson, yeah?
Hello, welcome back. In this lesson, we're going to see how to calculate the DFT. There are three ways we can calculate the DFT. We can calculate the DFT using simultaneous equations, or by correlation, which involves detecting a known waveform in another waveform, or by using the fast Fourier transform method, which is often known as FFT. In this course, we are going to focus on using the FFT. Using simultaneous equations is very tiring. Imagine having n values from the time domain which you want to calculate n values of the frequency domain for. This means you have to solve for n unknowns, and therefore you must write n linearly independent equations. This gets very messy after some time. A more standard way to calculate DFT is by correlation. Let's try to calculate the DFT of a 64-point signal. This means we need to calculate 33 points in the real part and 33 points in the imaginary part of the frequency domain. Let's see how to calculate one of the 33 points. Let's take point 3, which is IMX3. This is the amplitude of the sine wave that makes 3 complete cycles between the points 0 and 63. This is our 64-point signal. This is just a sine wave which makes 3 cycles between 0 and 63. Let's take another 64-point time domain signal, x2, like this. What we are going to do is find out whether the same basis function, S3, exists in both of them. We shall use this example to demonstrate what the DFT correlation algorithm we shall develop should do. Like I said, the basis function we are looking for is S3. And as we can see, this function completes exactly 3 cycles from 0 to 63. And we can see again that this basis function exists in x1. In fact, it's the same as x1. However, it does not exist in x2. When our correlation algorithm computes x1, it must produce a value of 32, which represents the amplitude of the sine wave present in the signal. In contrast, when the algorithm computes x2, a value of 0 must be produced, indicating this particular sine wave is not present in the signal. Correlation is used to detect a known waveform contained in another waveform. The single number that results from this procedure is a measure of how similar the two signals are, and we perform correlation by multiplying the signal being analyzed by the signal we are looking for and adding all points in the resulting signal. The sum of all points produced by x1 times s3 is 32, and the sum of all points produced by x2 times S3 is 0. This is just the correlation of S3, the sample in the frequency domain, which makes exactly 3 complete cycles. We can calculate for other samples such as S5, S6, S7, etc. using the same method. This entire procedure is put together in the form of the analysis equation. This is the equation for calculated DFT. In these equations, x of I is the time domain signal being analyzed, and Rex of k and Imx of k are the frequency domain signals being calculated. The index I runs from 0 to n-1, and the index k runs from 0 to n/2. This basically means each sample in the frequency domain is found by multiplying the time domain signal by the sine or cosine wave being looked for and adding the resulting point. So that's all there is for this lesson, and don't hesitate to leave your questions below. I'll see you in the next lesson.
Hello, welcome back. In this lesson, we're going to see how to compute the DFT of a signal in Matlab. So let's get started. So what we're going to do is we're going to take this 20 Hz signal, this 20_1 Hz signal that we've been working with, and we know the signal is in the time domain. Find the frequency domain of this signal and verify if indeed it's got 20 Hz and 1 Hz component. So let's get started. We start by importing the signal. I'm going to say input signal, input_signal equals load, and the signal is _20 Hz, _1 Hz, _sig.txt. And to find the DFT, we use a function in Matlab known as the FFT. FFT basically means Fast Fourier Transform. So the FFT is a very nice algorithm for computing the DFT very, very quickly. It's orders of magnitude faster than standard DFT algorithms. So you don't find people using DFT algorithms, although we have to understand how DFT is derived. Often when we are computing the discrete Fourier transform of a signal, we have to use the FFT algorithm, and the FFT is simply the fast Fourier transform. FFT actually should be called FDFT, meaning fast discrete Fourier transform, but it's been shortened to FFT. So anyway, Matlab uses the FFT function. So to get the discrete Fourier transform of this input signal, we can just say y. Let's store the output of the DFT computation into this vector known as y. So we can say y equals FFT input signal, signal like this, and it computes it. So it's computed. But the problem is, as you can see over here, it says this is a complex number. It's a complex double, so it's got real part and imaginary part. So we cannot plot y. What we have to do is we have to find the magnitude of y in order to be able to plot it, and the magnitude will make it plottable. So next, let's find the magnitude and the phase of this y, which is the frequency domain of the input signal. So I'm going to create another vector here. I'll say y mag equals, and the magnitude is as simple as abs y, the absolute value of y, like this, and then I'll hit enter. And to get a phase, we can say y phase. This is a variable to store the phase we'll use. say y phase equals unwrap, and then over here we say angle y. This will give us the phase. Okay, hit enter like this. So what we have to do now is plot the result we have. But before we plot all three on the same window, let's just examine y mag and see. I'm going to plot y mag, plot y mag, and I'm going to use color green like this. And this is what we have. This is the frequency spectrum we have. Right. So over here, we need to observe a bit more to be able to identify our various frequency components. So we've got 4 spikes here. The first thing you need to know is this side here is a mirror of this side here. So what we're truly interested in is half of what is shown here. You can see it's from 0 to 300, but what's of importance to us is just half of this, 0 to 150. That's how we view it. So I'm going to come over here, the zoom, I'm going to place it on 150 here, and I'm going to come over here like this and do this. Okay, so now this is the frequency spectrum we're working with. We have 0 over here, we have 150 over here, but these values do not represent frequency. The unit here is not frequency. Actually, we have to derive the unit on our own, and this is how we go by it. So because of the Nyquist theorem, we know the highest frequency to be represented in this frequency spectrum has to be the maximum, has to be at most half the sampling rate of the signal. And because we created this time domain signal ourselves and we know the sampling rate was set at 100 Hz, we know that half of 100 is 50. And because of Nyquist theorem, the highest frequency in the spectrum should be half the sampling rate. 100 divided by 2 is 50. Therefore, the highest frequency would be here. It would correspond to this side here. 150 is this side here. This 140, this 150. So we can just say 1, 2, 3, 4, 5, 6, 7, 8. And 50 divided by 8, we have 6.25. So from here to here is 6.25. And from here, so this side here is 6.25, and then when we get here, this becomes 12.5, and then we add 6.25, add 6.25. So if we estimate properly, you'd realize that from here to here, if this is 6.25, this side here corresponds to 1 Hz. So 0 is here, 0 Hz is here, 6.25 Hz is here, this is 1 Hz. And when we look at it closely and we get here, we realize that this will correspond to 20 Hz. So this is how, we know that indeed we've got our 1 Hz signal here and our 20 Hz by going through the sequence I just gave, by taking into account the sampling frequency and then using Nyquist theorem to know that then the highest frequency here has to be half the sampling rate. And with that, we can derive our various frequencies. So so anyway, that's how we take a look at this. If you have any questions, do send me a message or leave in the questions area. So now let's plot all 4 signals. I'm going to close this and I'm going to use a subplot. I'm going to say subplot. We have 3 signals. Subplot, we have 3 plots. So I'm going to say 3, 1, 1. And the first thing we're going to plot is going to be the input signal. And I'm going to say plot input underscore signal, and I'm going to give it a title. Input time domain signal. And then next, let's plot the magnitude. I'm going to say subplot 3, 1, 2. And what I'm going to do is plot Y mag. And I'm going to give it a title. magnitude, and then I'm going to say subplot 3, 1, 3. And I'm going to say plot into bracket y phase, and I'm going to give it a title phase, and I'm going to use the SHG to bring it in front, SHG like this. This is what we have. So we've just computed the DFT of the time domain signal, and like I said, we just take into account half of this spectrum here. This side here is mirrored over here, so all we need is to observe this. So this is all there is for this lesson on DFT. If you have any questions at all, just let me know or leave in the questions area. And if you're finding this course useful in any way, please take some time off to leave a review, and I shall see you in the next lesson.
Hello, welcome back. In DFT, the time domain and the frequency domain are completely symmetrical. The symmetry between the time and the frequency domains is called duality, and this gives rise to many interesting properties. For instance, a single point in the frequency domain corresponds to a sinusoid in the time domain. In the same way, a single point in the time domain corresponds to a sinusoid in the frequency domain. Also, convolution in the frequency domain corresponds to multiplication in the time domain, and in the same way, convolution in the time domain corresponds to multiplication in the frequency domain. These are some of the interesting properties produced by the symmetry between the time and frequency domains. I'll see you in the next lesson. Hello, welcome back. Like we have described so far, the frequency domain is a group of amplitudes of cosine and sine waves. This way of looking at it, which we have been using so far, is what is known as the rectangular notation. Alternatively, the frequency domain can be expressed in the polar form. In the polar form, Rex of k and Imx of k are replaced with magnitude x of k and phase x of k as expressed here. And all polar notation points can be derived from rectangular notation. Now let's see how to derive the polar notation from the rectangular notation. When we add a cosine wave and a sine wave of the same frequency, the result is a cosine wave with a different amplitude and a phase shift. The information held in A and B are transformed to m and theta. No information is lost in this process. A vector representation looks like this. We can calculate m using the Pythagorean theorem like this. And the angle theta is simply the arctangent of B over A. To calculate the magnitude and the phase of the polar notation given the rectangular notation, we simply replace A and B in the vector representation we just saw with Rex and Imx. This then gives us the equation for the magnitude and the phase, as simple as this. With this same equation, given the polar notation, we can use a simple change of subject to derive the rectangular notation like this. Rex of k equals magnitude x of k multiplied by cosine phase x of k, and Imx of k equals magnitude x of k multiplied by the sine phase x of k. As simple as this. The rectangular and polar notations allows us to see DFT from two different perspectives. The rectangular notation allows us to view DFT in terms of amplitudes, while the polar notation offers both amplitude and phase shift. Although both notations represent the same information, there are instances where one is easier to use than the other. For instance, these graphs show the same frequency domain signal represented in both rectangular notation and polar notation. This is a low-pass filter with a 0.2 F cutoff frequency. As we can see, in this case, the polar notation provides us with a better understanding of the characteristics of the signal. In comparison, the rectangular form is almost always used in mathematical computations. Because of this, we can conclude that the rectangular notation is usually best for calculation, such as in computer algorithms, whereas the polar notation is best for communicating among ourselves and other engineers. So this is all there is, and if you have any questions, do let me know, and I'll see you in the next lesson. Hello, welcome back. In digital signal processing, DFT is used to perform three tasks, mainly spectral analysis, frequency response, and signal processing. We shall take a look at these three procedures, starting with spectral analysis. In spectral analysis, the three most important parameters of a waveform are the phase, the frequency, and the amplitude, and we use DFT to extract. Let's say we have a 256-point sound data we acquired with our microphone like this. All we can see are the stages, mostly noisy waveform that carries little information. Now let's say we take this measured signal and multiply it by a Hamming window. Don't worry much about Hamming window. We have got an entire section dedicated to digital filter design and windows. For now, Hamming window is just a smooth curve like displayed over here. So after multiplying our measured signal with the Hamming window, this is what our windowed signal looks like. This results in a 256-point signal where the samples near the ends have been reduced in amplitude. When we take the DFT of this windowed signal and convert to the polar notation, we get this frequency spectrum. This still looks noisy, however, averaging 100 of the frequency spectra produces something we can work with, like this. Now the noise has been reduced drastically. Now let's analyze this spectrum over here. Three types of features appear in the spectra of the acquired signals. The first feature is random noise, such as white noise. The second feature is interference from power lines, switching power supplies, radios, TVs, etc. And the third feature is the real signals we are looking for. They usually appear as fundamental frequencies plus harmonics. Here, the real signal we are looking for is 13 Hz. The harmonics of 13 Hz is any frequency which is a multiple of 13. Over here, the harmonics are 26 and 39. So this is where our signal has landed, and this one is clearer to work with. And looking at these various features is what is known as spectral analysis. So we shall build on this practically. And this is all there is for this lesson, and I shall see you in the next lesson. Hello, welcome back. As we saw earlier, systems are analyzed in the time domain using convolution. In frequency domain, DFT can be used. As we have already seen, using Fourier transform, every input signal can be represented as a group of sine and cosine waves, each with a specified amplitude and phase shift. This means that any linear system can be completely described by how it changes amplitude and phase of cosine and sine waves passing through it. This information is what is known as the frequency response. Since both the impulse response and the frequency response contain complete information about a system, there must be a one-to-one correspondence between the two. Given one, we should be able to calculate the other. Let's explore that relationship. A system's frequency response is the Fourier transform of its impulse response. Impulse response use lowercase variables, while corresponding frequency response use uppercase variable. So a lowercase h is a common symbol for impulse response, and therefore uppercase h is used for frequency response. Systems are described in the time domain by convolution. X of n convolved with h of n gives us y of n. This is the system description. In the frequency domain, input spectrum is multiplied by the frequency response, resulting in the output spectrum, as simple as this. In an equation form, capital X of n times capital H of n equals capital Y of n. Like we saw in the previous lesson, convolution in time domain corresponds to multiplication in the frequency domain. And these arrow here just indicates the DFT and inverse DFT relationship between the two domains. If we have a system's impulse response, by using DFT, we can simply derive the frequency response. If we want a higher resolution frequency response, we can pad the impulse response with zeros. Let's say the 64-point signal is a system's impulse response. Obviously, looking at this wave is not going to give us enough information. Taking a 64-point DFT of this impulse response produces the frequency response. Now the system becomes more understandable. We can describe the system as a bandpass filter which passes frequencies between 0.2 and 0.3 Hz and reject all other frequencies. Due to the low number of samples, we find this curve not very smooth. We can improve the situation by padding the impulse response with zeros before taking the DFT. If we take this 64-point impulse response and pad it with zeros to make it 512 points, this is what it will look like. Now, we can take the DFT of this 512-point impulse response. This will be the frequency response produced, the same frequency response with a smoother curve. So this raises the question of how much resolution can be obtained in the frequency response. This answer is infinitely high. If we are willing to pad impulse response with an infinite number of zeros, meaning there is nothing limiting the frequency response except the length of the DFT. One other way of looking at it is, even though the impulse response is discrete, the corresponding frequency response is continuous. So this is all there is to it for now, and if you have any questions, do let me know, and I'll see you in the next lesson. Hello fellas, welcome back. So in this section we shall give a very brief overview of complex numbers before we start using them in fast Fourier transform and other DSP applications. So complex numbers are an extension of ordinary numbers used in everyday mathematics. With complex numbers, we are able to manipulate two variables as a single quantity. In mathematical equations, a complex number is represented by a single variable, though it is composed of two parts. Let's take a look at a complex plane. Every complex number has a unique location in the complex plane. The horizontal axis represents what is known as the real part, and the vertical axis represents what is known as the imaginary part. The three complex variables in the complex plane can be written as a equals 2 plus 6j, b equals minus 4 minus 1.5j, c equals 3 minus 7j, where a, b, and c are complex variables. The mathematical notation for separating a complex number into its real and imaginary parts uses re and im operators. Complex variables a, b, and c can be separated into real and imaginary parts like this. We perform the same algebraic operations we perform on ordinary numbers on complex numbers as well. Into bracket a plus bj plus into bracket c plus dj equals a plus c plus j into bracket b plus d. Very straightforward. In the same way we perform subtraction. Into bracket a plus bj minus into bracket c plus dj equals into bracket a minus c plus j into bracket b minus d. Very straightforward. So this is a very short overview of complex number system. In the next lesson we shall see how to represent complex numbers in the polar notation, and I shall see you in the next lesson. Hello, welcome back. Complex numbers can be represented in polar notation as well, and just like ordinary numbers we can easily convert between polar notation and rectangular notation. As we mentioned earlier, any complex number such as a has real part REA and imaginary part IMA. To convert complex A to polar notation, we need to find the magnitude M and the phase theta. We find the magnitude by simply computing the square root of REA squared plus IMA squared. We compute the phase angle by finding the arctangent of IMA over REA. Similarly, if we have the magnitude and the phase angle of the complex number, we can find the rectangular representation of the complex number. To find the real part of a complex number, given the magnitude and the phase angle, we simply compute n times the cos of theta, meaning we simply multiply the magnitude by the cosine of the phase. To find the imaginary part, we compute m times sine theta. A complex number written in the rectangular notation is written in the form a plus jp, and this is equal to m times cos theta plus j sine theta. In the rectangular notation, the key information is carried in a and b, and in the polar notation, the key information is carried in m and theta. I hope you understand. Do let me know if there's something you don't understand. One of the most useful equations in complex mathematics is Euler's relation e to the power j times x equals cos x plus j sine x. The complex exponential equation over here can be rewritten in the form m times e to the power j theta equals a plus jb. And the left part in this equation represents the rectangular form and the right part the exponential polar form. As we shall see later, the complex exponential representation is widely used in DSP. Multiplication of complex exponential is very straightforward. If we have two complex exponentials, m1 e to the power j theta 1 multiplied by m2 e to the power j theta 2, and we multiply these two complex numbers, we'll get m1 times m2 e to the power j into bracket theta 1 plus theta 2. Very straightforward. Division of complex exponentials is performed like this. We divide m1 over m2, like we do in ordinary algebra. But when dealing with exponents, just like multiplication becoming addition, division becomes subtraction, like it's shown here. So that's all there is. Leave your questions below or send me a message, and I'll see you in the next lesson. I hope you understand. Do let me know if there's something you don't understand. Hello fellas, welcome back. Complex numbers are massively used in electronics and DSP because they give us a much more compact way to represent and manipulate sine and cosines. The most conventional way to represent a sinusoid is a cos into bracket omega x plus b sine into bracket omega x. And note that over here, omega is equal to 2 pi f, and omega here represents the natural frequency, which is in radians. If we want to get omega in the units of hertz, it's equal to 2 pi f. So a cos into bracket omega x plus b sine into bracket omega x is equivalent to a plus jb, where capital A is equivalent to lowercase a, and this represents the amplitude of the cosine wave, and uppercase b here is equivalent to the negative lowercase b, and this represents the negative amplitude of the sine wave. Sine waves become the imaginary part. It is also important to understand that this is not an equation, but just a way of letting a complex number represent a sinusoid. This expression over here can be written in the polar notation as well. M cos into bracket omega t plus phi is equivalent to m e to the power j theta. Over here, m is equivalent to m, and this represents the amplitude of the cosine wave, and theta is equivalent to the negative of phi, and this represents the negative amplitude of sine wave. So this is the same information represented in the polar notation. So this is all there is to it. If you have any questions, don't hesitate at all to send me a message or leave your questions below, and I'll see you in the next lesson. Have a good one. Hello, welcome back. In this lesson, we're going to take a look at how complex numbers can be used to represent systems. Let's say we have this continuous input signal, 3 cos into bracket omega t plus pi over 4. When we write this in complex notation, it becomes 3e to the power minus j pi over 4. Let's say this input signal is passed through a system whose characteristics is described by the equation 0.5e to the power 3e over 8. When this input signal passes through the system, it produces a signal of this characteristics. A signal described by complex notation 1.5e to the power j theta over 8. Or in the rectangular notation 1.5 cos into bracket omega t plus theta over 8. This example is just to show that the system, the input signal as well as the output signal, can all be represented and computed in complex notation. And just like we demonstrated before, if we are not comfortable with the complex notation, we can convert everything into the rectangular notation like we've shown here. We've got a rectangular form as well as the complex form. So the takeaway from this lesson is that
we can represent our linear systems in complex numbers as well. So that's all there is for this lesson, and I will see you in the next lesson.
Hello, welcome back. So all the four members of the Fourier transform family can be carried out with real numbers or complex numbers. In this lesson, we shall see how to change the parameters of our real DFT equation to complex numbers. This is the real DFT equation. By real, I mean it uses real numbers. We described this as the forward transform, calculating the frequency domain from the time domain. Although it uses real and imaginary parts, these equations only involve ordinary numbers. The frequency index k runs from 0 to n over 2. These are the same equations as the ones we used in the DFT section, except that in this new form, the term 2 over n has been included. Basically, these equations say an n sample time domain signal x of n is decomposed into a set of n over 2 plus 1 cosine waves and n over 2 plus 1 sine waves with frequencies given by the index k. The amplitudes of the cosine waves are contained in Rex of k, while the amplitude of the sine waves are contained in Imx of k. Although we use real parts and imaginary parts, there are no complex numbers involved in these equations. As you can see, there is no j here at all. Also, we have included what is known as the normalization factor 2 over n to this equation. So this is all there is for this lesson, and if you have any questions, do leave them below, and I shall see you in the next lesson. Hello guys, welcome back. So our first step to show how sine and cosine waves can be written in a complex equation form is to invoke Euler's notation, which is given by e to the power jx equals cos x plus j sine x. With a bit of algebra, we can rewrite the equation in two forms to derive cos x equals e to the power jx plus e to the power minus jx all over 2 and sine x. Euler's relation gives us a way to write equations between complex numbers and sinusoids. When we change the terms, we get cosine omega t equals 1 over 2 times e to the power j minus omega t plus 1 over 2 times e to the power j omega t. Sine omega t becomes 1 over 2 times e to the power j minus omega t minus 1 over 2 times e to the power j omega t. Over here, each expression is the sum of two exponentials, one containing a positive frequency omega and the other containing a negative frequency minus omega. When sine and cosine waves are written as complex numbers, the negative portion of the frequency spectrum is automatically included. The positive and negative frequencies are treated equally. It requires 1/2 of each to form a complete waveform. So that's all there is to it. And if you have any questions, as usual, just leave them below or send me a message, and I shall see you in the next lesson. The complex DFT equation is expressed in polar notation by this equation here, like this. Both the time domain lowercase x of n and the frequency domain uppercase x of n are an array of complex numbers with k and n running from 0 to capital N minus 1. Alternatively, we can use Euler's relation to rewrite the complex DFT equation in rectangular form like this. Now, let's compare the complex DFT equation we have now to the real DFT equation we saw earlier. Let's compare using the rectangular notation. The real DFT converts a real time domain signal x of n into two real frequency domain signals Rex of k and Imx of k. In the complex DFT, both the time domain signals x of n and the frequency domain signal capital X of k are arrays of complex numbers. Even though the time domain signals of the complex DFT is a complex array, as we shall see, there is nothing that requires us to use the imaginary part. For example, if we were processing a signal like a series of voltage measurements over time, the actual signal data becomes the real part of the time domain signal, while the imaginary part is composed of zeros. Moving on with our comparison, The real DFT only deals with the positive frequencies, meaning the frequency domain index k only runs from 0 to n/2. In comparison, the complex DFT includes both the positive and negative frequencies. This means k runs from 0 to n-1. The frequencies between 0 and n/2 are positive, while the frequencies between n/2 and n-1 are negative. Remember, the frequency spectrum of a discrete signal is periodic, making the negative frequencies between n/2 and n-1 the same as minus n/2 and 0. Also, the real DFT has a scaling factor of 2 in front of it, as we can see over here, while the complex DFT does not have. For example, let's say we are taking the real DFT of a cosine wave with an amplitude of 1. The spectral value corresponding to the cosine wave will also be 1. If we repeat the same process using complex DFT, the cosine wave corresponds to 2 spectral values, a positive and a negative frequency. Both of these frequencies have a value of 1/2, meaning a positive frequency with an amplitude of 1/2 combines with a negative frequency with an amplitude of 1/2, producing a cosine wave with an amplitude of 1. Like the real DFT and the inverse DFT, the complex DFT also has the inverse complex DFT, which is expressed like this. Also, I should mention, you need not worry about remembering all the equations in this course, unless you're a mathematician who is going to be working with signals and systems using pen and paper. We as programmers don't need to memorize these equations. We don't also need to know how to derive them. We just have to keep them somewhere safe, and whenever our algorithm is not working as expected, we just plug our values in these equations and try to sort of reverse engineer using pen and paper. So that's all there is for this particular lesson. If you have any questions, let me know, and I shall see you in the next lesson. Hello, welcome back. So the FFT algorithm is a very complicated algorithm, and the details are usually left to those who are specialized in the field. So in this lesson, we just give a general overview of how the FFT algorithm operates without taking into account things like the use of complex numbers. So in complex notation, the time and frequency domains each contain one signal made of n complex points. Each of these complex points is composed of 2 numbers, the real part and the imaginary part. For example, when we talk about complex sample x of 0, we're referring to the combination of RE x of 0 and IM x of 0. In other words, each complex variable holds 2 numbers. When 2 complex variables are multiplied, the 4 individual components must be combined to form 2 components of the product. So in this lesson, when I use singular terms like signal, point, sample, or value, I'm referring to the combination of the real part and the imaginary part of the system. So FFT works by decomposing an n-point time domain signal into n time domain signals, each composed of a single point. The second step is to calculate the n frequency spectra corresponding to these n time domain signals. And lastly, the n spectra are synthesized into a single frequency spectrum. So if someone asks you, how does FFT work? It's as simple as decomposing an n-point time domain signal into n time domain signals, each composed of a single point, and then finding the n frequency spectra corresponding to these n time domain signals, and then synthesizing the n spectra into a single frequency spectrum. It's as simple as that. This is FFT in plain language. So this image over here shows a time domain decomposition used in the FFT. In this example, a 16-point signal is decomposed through 4 separate stages. The first stage breaks the 16-point signal into 2 signals, each consisting of 8 points. The second stage decomposes the data into 4 signals of 4 points.
This pattern continues until there are n signals composed of a single point. An interlaced decomposition is used each time a signal is broken in two, that is, the signal is separated into its even and odd number samples. There are log 2n stages required in this decomposition, and what this means is a 16-point signal requires 2 to the power 4, given as 4 stages. A 512-point signal requires 7 stages because 2 to the power 7, and a 4096-point signal requires 12 stages. Decomposition also involves reordering of the samples in the signal. This diagram over here shows the rearrangement pattern required. On the left, the sample numbers of the original signal are listed along with their binary equivalents. On the right, the rearranged sample numbers are listed also with their binary equivalents. The important idea here is that the binary numbers are the reversals of each other. For example, sample 3, which has the binary number 0011, is exchanged with sample number 12, which has the binary number 1100. Likewise, sample number 14, which has the binary number 1110, is swapped with sample number 7, which has the binary number 0111, and so forth. The FFT time domain decomposition is usually carried out by bit reversal sorting algorithm. This involves rearranging the order of the n time domain samples by counting in binary with the bits flipped left for right, just like we see over here. The next step in the FFT algorithm is to find the frequency spectra of the 1-point time domain signals. Nothing could be easier. The frequency spectrum of a 1-point signal is equal to itself. This means that nothing is required to do this step. Although there is no work to do, we must still remember that each of the 1-point signal is now frequency spectrum and not a time domain signal. The last step in the FFT is to combine the n frequency spectra in the exact reverse order that the time domain decomposition took place. This is where the algorithm gets messy. Unfortunately, the bit reversal method cannot be used over here, and we must go back one stage at a time. In the first stage, 16 frequency spectra, 1 point each, are synthesized into 8 frequency spectra, 2 points each. In the second stage, the 8 frequency spectra, 2 points each, are synthesized into 4 frequency spectra, 4 points each, and so on. The last stage results in the output of the FFT, a 16-point frequency spectrum. This slide shows how 2 frequency spectra, each composed of 4 points, are combined into a single frequency spectrum of 8 points. This synthesis must reverse the interlaced decomposition done in the time domain. In other words, the frequency domain operation must correspond to the time domain procedure of combining 2 4-point signals by interlacing. So consider 2 time domain signals ABCD and EFGH. An 8-point time domain signal can be formed by 2 steps. First, we dilute each 4-point signal with zeros to make it an 8-point signal, and then add the signals together. This means ABCD becomes A0, B0, C0, D0, and EFGH becomes 0E, 0F, 0G, 0H. Adding these 2 8-point signals produces AEBFCGDH. So from this slide, we can see that diluting the time domain with zeros corresponds to a duplication of the frequency spectrum. Therefore, in other words, the frequency spectra are combined in the FFT by duplicating them and then adding the duplicated spectra together. In order to match up properly when added, the 2 time domain signals are diluted with zeros in slightly different way. In one signal, the odd points are 0, while in the other signal, the even points are 0. In other words, one of the time domain signals is shifted to the right by 1 sample. Hence, we have 0E, 0F, 0G, 0H. This time domain shift corresponds to multiplying the spectrum by a sinusoid. And to understand this, we must remember that a shift in the time domain is equivalent to
convolving the signal with a shifted delta function. This multiplies the signal's spectrum with the spectrum of the shifted delta function, and the spectrum of a shifted delta function is a sinusoid. This is the FFT synthesis flow diagram. This shows the method of combining two 4-point frequency spectra into a single 8-point frequency spectrum. The times x operation means that the signal is multiplied by a sinusoid with an appropriately selected frequency. So this is all there is for this lesson, and send me a message if you have any questions, and I shall see you in the next lesson. Hello, welcome back. In the previous lesson, we learned that the n-point complex DFT equation for a sequence x of n is expressed like this. I'll just give a quick summary of the number of multiplications and additions required to calculate the DFT of a sequence using this equation. So for each DFT coefficient x of k, we should calculate n number of terms, including x of 0 times e to the power minus j 2 pi over n times k times 0, x of 1 times e to the power minus j 2 pi over n times k times 1, all the way to x of n minus 1 times e to the power minus j 2 pi over n times k times n minus 1. And after we've done this calculation, we have to calculate the summation. X of n is a complex number in general, and hence each DFT output needs approximately n complex multiplications and n minus 1 complex additions. A single complex multiplication itself requires 4 real multiplications and 2 real additions. Moreover, a complex addition itself requires 2 real additions, and therefore each DFT coefficient requires 4n real multiplications and 2n plus 2 into bracket n minus 1, which is equal to 4n minus 2 real additions. To have all the DFT coefficient, we have to compute this above equation for all n values of k. Therefore, an n-point DFT analysis requires 4n squared real multiplications and n times 4n minus 2 real additions. Don't worry about all of this. This is just to put to you how much calculation is really required to do this work. The important point is that the number of calculations of an n-point DFT is proportional to n squared, and this can rapidly increase with n. This plot over here shows the number of real multiplications versus the DFT length, n. Several algorithms have been developed to reduce the amount of computation required for dealing with DFT. One of the very popular, very efficient methods is the FFT, known as Fast Fourier Transform. We shall see how to work with FFT in this section. Let's say x of n is a sequence of length 8. Using the above equation, we can find the 8-point DFT of x of n as follows. X of k equals x of 0 times e to the power minus j 2 pi over 8k 0 plus x of 1 times the complex exponential all the way through x of 7 times the complex exponential. You can see this. Our goal is to examine the possibility of rewriting this 8-point DFT in terms of two DFTs of smaller length. We see that the length of the DFT, n equals 8 in this case, appears as the denominator in the complex exponentials. This leads us to the idea that what if we choose and group some of the terms of the equation in a way that allows us to simplify the fractions minus j2 pi over 8 kn. In this way, we may extract a DFT of smaller length out of the equation. In our case, since n is an even number, which is 8, we can choose all the terms with an even sample index. That is x of 0, x of 2, x of 4, and x of 6. When we select just these terms from the equation becomes this. So after simplifying the fractions in the complex exponential, we get this as the equation. If you compute this and simplify it, equation 4 is what we derive. So if we compare equation 4 over here to the full equation, which consists of
x of 0 through x of 7, we realize that what we have here as equation 4 and calling it g of k is a 4-point DFT of x of 0, x of 2, x of 4, and x of 6. So far, we have shown that half of the computation in the previous equation can be replaced with a 4-point DFT. But how can we simplify the rest of the calculations? The remaining terms, which corresponds to the odd index samples, are given by this, h1 of k. And this corresponds to x of 1, x of 3, x of 5, and x of 7. To simplify the fractions minus j2 pi over 8kn, we can simply factor out the complex exponential, and we obtain this. Hence, we have this third equation, equation 7, as the final equation, h1 of k. Again, if we compare this with equation 1, we observe that h1 of k is obtained by multiplying the complex exponential e to the power minus j2 pi over 8k by 4-point DFT x of 1, x of 3, x of 5, and x of 7. You see the magic going on there. We obtain h1 of k by multiplying the complex exponential by the 4-point DFT x of 1, x of 3, x of 5, and x of 7. Hence, we have achieved the goal of decomposing an 8-point DFT into two 4-point ones. I hope you understand. If you don't understand, just watch the video again. And really, if you don't understand all these equations and these derivations, it doesn't matter. Programmers out there don't know how these things are derived. We just use the functions. And like I said in the introduction, this section is just for people who want to know more about some of the topics. Yeah. So if we take this bracket part of the equation h1 of k and we rename just this part, the part within the bracket, we rename it as a new equation called just h of k, then the final result becomes x of k equals g of k plus e to the power minus j2 pi over 8k times 1 times h of k. Remember, this first term here, g of k, we saw it, this is the part that represents the even terms, and this second term here represent the odd terms. And remember, the odd terms, we had this part in the bracket and this was factored out. So like it's shown over here, g of k shows the even terms, h of k shows the odd terms, and then h of k multiplied by this gives us the full odd terms. I know you get it from the previous slide. Here, g of k and h of k corresponds to 4-point DFTs. We will soon discuss the flow graph of the decomposition we've just done. But I guess you're wondering, how does this reduce the number of multiplications and additions required for the full computation? So far, we've not reduced the number of multiplications. The number of multiplications required and additions required to compute x of k over here is the same as the number required using the normal DFT equation. We have only rearranged the terms and changed the coefficient of the multiplications, but we have not omitted any multiplications yet. To solve this issue, we have to note 3 points. First, the discrete complex exponential e to the power minus j2 pi over nkn is a periodic function of k with a period of n. Secondly, the range of k in our discussion is from 0 through 7. And finally, while the equation we saw, the first equation, the normal DFT equation, is in terms of complex exponential with period of 8, as you can see over here, named as equation 2. Equation 2 is in terms of complex exponentials with a period of 8. Hence, we have e to the power minus j2 pi over 8kn. Equation 9 over here, the new one, is basically in terms of 4-point DFTs, g of k and h of k, which are summations of complex exponentials with period of 4. This periodic behavior allows us to reduce the overall computation when computing all the DFT coefficients. For example, when calculating both x of k and x of k plus 4, we have to evaluate the terms of equation 2 twice. However, based on equation 9, we can get these two equations. We get x of k for this and then x of k of 4 with this equation.
Since g of k and h of k are periodic with 4, equation 11 will give us this equation. Comparing equation 12 and equation 10 clarifies how breaking an 8-point DFT into two 4-point DFTs allows us to use almost the same computation for both x of k and x of k plus 4, and significantly decrease the number of calculations through the periodicity property. So, in conclusion, while using the definition of DFT, which is the normal DFT equation, we need to perform 4n squared, which is equal to 256 real multiplications for an 8-point DFT. But with the algorithm we just discussed, which is the fast Fourier transform, we need to perform two 4-point DFTs along with n complex multiplications. For the two 4-point DFTs, we need to perform a total of 2 times 4 times n over 2 squared, and this gives us 128 real multiplications. The n extra complex multiplications requires 4n, and 4n here, n is 8, gives us 32 real multiplications. Hence, the fast Fourier transform method we just showed requires a total of 160 real multiplications, which is much smaller than that of the direct computation method of DFT. This is a considerable improvement, but we can achieve further simplification by applying the discussed fast Fourier transform method. It goes very deeper to reduce this amount of computation. So this is all there is for this lesson, and if you don't understand what is discussed here, don't worry. Like I said, the majority of people who use the FFT algorithm do not have an idea of how it works at all, so you need not worry. But if you want to learn more about this, I'll attach some reference materials, and yeah, you can watch the video over and over again or send me a message. In the next lesson, we'll continue to talk more about fast Fourier transform, and I shall see you in the next lesson. Hello, welcome back. In this lesson, we shall learn how to design digital filters. Digital filters are a very important part of DSP. In fact, their extraordinary performance is one of the key reasons that DSP has become so popular. Digital filters are used for signal separation and signal restoration. Signal separation is needed when a signal has been contaminated with interference, noise, or other signals. For instance, imagine a device for measuring the electrical activity of a baby's heart, something like ECG, while the baby is still in the womb. The raw signal will likely be corrupted by the breathing and heartbeat of the mother. A filter might be used to separate these signals so that they can individually be analyzed. Signal restoration is used when a signal has been distorted in some way. For example, an audio recording made with poor equipment may be filtered to better represent the sound as it actually occurred. Another example is the blurring of an image acquired with an improperly focused lens or a shaky camera. These problems can be solved with both analog and digital filters. So you might wonder which is better. Well, analog filters are cheap, fast, and have a large dynamic range, both in amplitude and frequencies. In this section, we shall go deeper into the merits of both filter types. Also, I should point out that in DSP, it is very common to say that filters' input and output signals are in the time domain. This is because signals are usually created by sampling at regular intervals of time, but this is not the only way sampling can take place. The second most common way of sampling is at equal intervals in space. For example, imagine taking simultaneous readings from an array of strain sensors mounted at 1 centimeter increments along the length of an aircraft wing. Many other domains are possible. However, time and space are by far the most common. When you see the term time domain in DSP, remember that it may actually refer to samples taken over time, or it may be a general reference to any domain that the samples are taken in. Every linear filter has an impulse response, a step response, and a frequency response. Each of these responses contains complete information about the filter, but in different form. If one of their three is specified, the other two are fixed and can be directly calculated. All three of these representations are important because they describe how the filter will react under different circumstances. The step response can be found by discrete integration of the impulse response. The frequency response can be found from the impulse response by using the fast Fourier transform and can be displayed either on a linear scale or in decibels. The most straightforward way to implement a digital filter is by convolving the input signal with a digital filter's impulse response. All possible linear filters can be made in this manner. When the impulse response is used this way, filter designers give it a special name, and this is called the filter kernel. Filters can also be designed by recursion. When a filter is implemented by convolution, each sample in the output is calculated by weighting the samples in the input and adding them together. Recursive filters are an extension of this, using previously calculated values from the output besides points from the input. Instead of using a filter kernel, recursive filters are defined by a set of recursion coefficients, and we shall see how to design recursive filters later in this course. For now, you need to know that all linear filters have an impulse response, even if we don't use it to implement the filter. To find the impulse response of a recursive filter, we simply feed in an impulse and see what comes out. The impulse response of recursive filters are composed of sinusoids that exponentially decay in amplitude. In principle, this makes their impulse responses infinitely long. However, the amplitude eventually drops below the round-off noise of the system, and the remaining samples can be ignored. Because of this characteristic, recursive filters are called the infinite impulse response, or IIR filters. In comparison, filters carried out by convolution are called finite impulse response, or FIR filters. As we saw in earlier sections, the impulse response is the output of a system when the input is an impulse. In the same way, the step response is the output when the input is a step, also known as an edge, and therefore an edge response. Since the step is the integral of the impulse, the step response is the integral of the impulse response. This provides two ways to find the step response. One will be to feed a step waveform into a filter and see what comes out, or to integrate the impulse response. Although technically integration is used with just continuous signals, with discrete signals we call discrete integration the running sum. The frequency response can be found by taking the DFT using the FFT algorithm of the impulse response. The frequency response can be plotted on a linear vertical axis or on a logarithmic scale with unit of decibels. The linear scale is best at showing the passband ripple and the roll-off, while the decibel scale is needed to show the stopband attenuation. In the next lesson, we shall give a quick review of the log scale and decibels. I'll see you in the next lesson. Hello, welcome back. So, a bell means that power is changed by a factor of 10, and it's named in honor of Alexander Graham Bell. For example, an electronic circuit that has 4 bells of amplification produces 10 times 10 times 10 times 10, basically 10 to the power of 4 amplification, therefore 10,000 times the power of the input. A decibel is 1/10 of a bell, therefore the decibel values of minus 20 dB, minus 10 dB, 0 dB, 10 dB and 20 dB means the power ratios of 0.01, 0.1, 1, 10, 100 and so on. I hope you get the order. In other words, every 10 decibels means the power has changed by a factor of 10. Over here, we must note that we're talking about change in power, not amplitude. For instance, imagine an amplifier with 20 dB of gain. By definition, this means that the power in the signal has increased by a factor of 100. Since amplitude is proportional to the square root of power, the amplitude of the output is 10 times the amplitude of the input, while 20 dB means a factor of 100 in power, it only means a factor of 10 in amplitude. Every 20 decibels means that the amplitude has changed by a factor of 10. In equation form for power, dB equals 10 log 10 P2 over P1, and in amplitude 20 log 10 A2 over A1. We can also express the equation using the natural log as shown on the right hand side over here. Since decibels are a way of expressing the ratio between two signals, they are ideal for describing the gain of a system, meaning the ratio between the output and the input signal. However, engineers also use decibels to specify the amplitude or power of a single signal by referencing it to some standard. For example, the term dBV means the signal is being referenced to a 1 volt RMS signal. Don't worry much about that, but what will be familiar to you will be the 3 dB, which means the amplitude is reduced by 0.705. And this 3 dB we spoke about when we're talking about analog filters. As a visual example, this is the same signal displayed in the linear scale and the logarithmic scale. We've got the frequency response in the normal linear scale and the frequency response in the decibels. As you can see, you can think of the decibels as a zoomed in version of the linear scale. So we use this to show more detail into a signal. So that's all there is for this lesson, and I shall see you in the next lesson. Hello, welcome back. One of the important parts of any DSP task is understanding how information is contained in the signals we are working with. There are two common ways of information representation. We have the time domain representation and the frequency domain representation. Information represented in the time domain describes when something occurs and what the amplitude of the occurrence is. For example, imagine an experiment to study the light output from the sun. The light output is measured and recorded once each second. Each sample in the signal indicates what is happening at that instant and the level of the event. If a solar flare were to occur, the signal directly provides information on the time it occurred, the duration, the development over time, etc. Each sample contains information that can be understood without reference to any other sample. Even if we have only one sample from this signal, we will know something about what we are measuring. This is the simplest way for information to be contained in the signal. In contrast, information represented in the frequency domain is more indirect. Many things in the universe show periodic motion. For example, a wine glass struck with the finger will vibrate, producing a ringing sound. A pendulum from a clock will swing back and forth. Stars and planets rotate on their axes and revolve around each other, and so forth. By measuring the frequency, the phase, and the amplitude of this periodic motion, information can often be obtained about the system producing the motion. Suppose we sample the sound produced by, ringing the wine glass, just hitting the wine glass with your finger. Suppose we sample the information from this signal. The fundamental frequency and the harmonics of the periodic vibration relate to the mass and elasticity of the material. A single sample in itself contains no information about the periodic motion, and therefore no information about the wine glass. The information is contained in the relationship between many points in the signal. So this brings us to the importance of the step and frequency responses. The step response describes how information represented in the time domain is being modified by the system. In contrast, the frequency response shows how information represented in the frequency domain is being changed. This distinction is absolutely important in filter design because it is not possible to optimize a filter for both applications. Good performance in the time domain results in poor performance in the frequency domain, and vice versa. So, for example, if we are designing a filter to remove noise from an ECG, and over here note that ECG information is represented in the time domain, In this case, the step response is the important parameter and the frequency response is of little concern to us. On the other hand, if our task is to design a digital filter for a hearing aid with the sound information being represented in the frequency domain, then the frequency response is all important while the step response doesn't matter. So I hope you get a difference here. Now let's look at what makes filter optimal for time domain and frequency domain applications. Welcome back. In this lesson, we shall take a look at some time domain parameters. So by now, it may be obvious why the step response is more important in time domain filters. You may be wondering why the impulse response isn't the important parameter. Well, the answer lies in the way the human mind understands and processes information. Remember that the step, impulse, and frequency responses all contain identical information, just in different arrangement. The step response is useful in time domain analysis because it matches the way humans view the information contained in a signal. For example, suppose you are given a signal of some unknown origin and you are asked to analyze the signal. The first thing you would do is divide the signal into regions of similar characteristics, and you can't stop yourself from doing this. Your mind will actually do it automatically. Some of the regions may be smooth, others may have large amplitude peaks, others may be noisy. This segmentation is accomplished by identifying the point that separates the regions. This is where the step functions come in. The step function is the purest way of representing a division between two dissimilar regions. It can mark when an event starts or when an event ends. It tells you that whatever is on the left is somehow different from whatever is on the right. This is how the human mind views time domain information. Essentially, the human mind views time domain information as a group of step functions dividing the information into regions of similar characteristics. The step response, in turn, is important because it describes how the dividing lines are being modified by the filter. To distinguish events in a signal, the duration of the step response must be shorter than the spacing of the event. This dictates that the step response should be fast as possible. As we can see over here, the image on the right has a fast step response compared to the one on the left. The common way to specify the rise time is to check the number of samples between 10% and 90% amplitude levels. You may be wondering, why isn't there a very fast rise time all the time? Why don't we get a fast rise time with every filter or with every design? There are many reasons. One could be noise reduction, and another could be inherent limitation of the data acquisition system, and a third reason could be avoiding aliasing and other things. So ideally, we want a fast step response like the image on the right. The ideal step response, of course, is the brick wall that we spoke about. These images also describe the time domain signal using a different parameter known as the overshoot. Over here, the image on the left has no overshoot, while the one on the right has overshoot. Overshoot must generally be eliminated because it changes the amplitude of samples in the signal. This is a basic distortion of the information contained in the time domain. Also, it is often desired that the upper half of the step response be symmetrical with the lower half. So if we take this as the middle, the upper half here, this side, should be symmetrical to this side. So as you can see, the image on the left has this behavior, whilst the image on the right hasn't got this behavior. This symmetry is needed to make the rising edges look the same as the falling edges. The symmetry is called the linear phase because the frequency response of this would have a straight line, therefore it's called the linear phase. So we must always remember these three parameters. They are very important in evaluating time domain filters. Remember the step response, overshoot, and phase linearity. So this is all there is for this lesson. In the next lesson, we shall take a look at some frequency domain parameters. I shall see you in the next lesson. Hello, welcome back.
There are four basic frequency domain parameters. These are the passband, the transition band, the stop band, and the roll-off. The passband refers to those frequencies that are passed, while the stop band contains those frequencies that are blocked. The transition band is between the passband and the stop band. A fast roll-off means that the transition band is very narrow. The division between the passband and the transition band is called the cutoff frequency, which we shall see. Here we have the four most common frequency responses. Frequency domain filters are generally used to pass certain frequencies while blocking other frequencies. The four responses are the low pass, the high pass, the band pass, and the band reject. To separate closely spaced frequency, the filter must have a fast roll-off, like the image shown on the right. For the passband frequencies to move through the filter unchanged, there must be no passband ripple, like the image on the right over here. We don't want the one on the left over here. And lastly, to adequately block the stop band frequencies, it is necessary to have a good stop band attenuation, again like the image on the right here. So this is all there is for this lesson, and I shall see you in the next lesson. Hello, welcome back. In this lesson we shall see how filters can be designed using spectral inversion. So the high pass, band pass, and band reject filters are designed by starting with a low pass filter and then converting the low pass filter into the desired response, which could be high pass, band pass, or band reject. For this reason, most discussions on filter design only gives example of low pass filters. There are two methods for the low pass to high pass conversion. There is the spectral inversion and there's the spectral reversal. Both are equally useful. Let's see the spectral inversion first. This is an example of spectral inversion. Over here we have a low pass filter kernel called the windowed sync, which we have a section dedicated for this windowed sync type filters, so don't worry much about that now. This filter kernel is 51 points in length, as you can see 0 through 50, which is shown in the upper left corner image over here. The corresponding frequency response is shown over here in the upper right corner, and it is found by adding 13 zeros to the filter kernel and then taking the 64-point FFT. Two things must be done to change the low pass filter kernel into a high pass filter kernel. Firstly, we must change the sign of each sample in the filter kernel and then add 1 to the sample at the center of symmetry. This results in the high pass filter kernel, which we have at the bottom left corner here, and with its frequency response by its side at the bottom right over here like this. Spectral inversion flips the frequency response top for bottom, changing the pass bands into stop bands and the stop band into pass band. In other words, it changes a filter from low pass to high pass to low pass, band pass to band reject, or band reject to band pass. Let's see why this two-step modification to the time domain results in an inverted frequency domain spectrum. Let's say we have an input signal x of n, and x of n is applied to two systems in parallel. One of these systems is a low-pass filter with an impulse response given by h of n, and the other system does nothing to the signal and therefore has impulse response that is a delta function, delta of n. The overall output y of n is equal to the output of the all-pass system minus the output of the low-pass system. And by the all-pass system here, I mean the system that does nothing to the signal, meaning all of the signal passes through, the one below here. Since the low frequency components are subtracted from the original signal, only the high frequency components appear in the output, and this gives us a high pass filter, really. And we can do this in code using two steps. First, we run the signal through a low pass filter and then subtract the filtered signal from the original. However, the entire process can also be performed in a single stage by combining the two filter kernels. We shall see this in future sections. Parallel systems with added outputs can be combined into a single stage by adding their impulse responses. We shall explore this later. In this next one, the filter kernel of the high-pass filter is given by delta of n minus h of n. And this means change the sign of all the samples and then add 1 to the sample at the center of symmetry. For this technique to work, the low frequency component exiting the low pass filter must have the same phase as the low frequency component exiting all pass system. Otherwise, a complete subtraction cannot take place. This places two restrictions on the method. One, the original filter kernel must have a left-right symmetry, meaning a zero phase or a linear phase, and two, the impulse must be added at the center of symmetry. So next, we shall take a look at the second method for low pass to high pass conversion, the spectral reversal method. So let's see that in the next lesson. Hello, welcome back. So just like we saw in the other example, this is a low pass filter kernel in the upper left corner of the screen, and on the right side we've got its frequency response. But over here the high pass filter kernel is formed by changing the sign of every other point. So we simply change the sign of every other point of the original filter kernel. And what this does is it flips the frequency domain left for right. So 0 becomes 0.5 and 0.5 becomes 0. The cutoff frequency of this example low pass filter is 0.15. This results in the cutoff frequency of the high pass filter being 0.35. Changing the sign of every other sample is equivalent to multiplying the filter kernel by a sinusoid with a frequency of 0.5 essentially. This has the effect of shifting the frequency domain by 0.5. When we observe these diagrams, we can see how low pass and high pass filter kernels can be combined to form a band pass and band reject filters. So I recommend you pause the video and try to understand what's going on here based on the previous example we saw. So in short, adding the filter kernels produces a band reject filter, while convolving the filter kernels produces a bandpass filter. These are based on the way cascaded and parallel systems are combined. Multiple combination of these techniques can also be used. For instance, a bandpass filter can be designed by adding two filter kernels to form a stop pass filter and then use spectral inversion or spectral reversal as previously described. All these techniques work very well. So to summarize these two diagrams, a bandpass filter can be formed in number 1 over here. A bandpass filter can be formed by cascading a low pass filter and a high pass filter. This can be reduced to a single stage. And in number 2 over here, the filter kernel of a single stage is equal to convolving of the low pass and the high pass filter kernels. Let's take a look at this one. This also shows the designing of a band reject filter. As shown over here, a band reject filter is formed by the parallel combination of a low pass filter and a high pass filter with their output added. In number 2 over here, this is reduced to a single stage with the filter kernel found by adding the low pass and the high pass filter kernels. So this is the end of this lesson, and if you have any questions, just send me a message. I'll see you in the next lesson. Hello, welcome back. This arrangement over here summarizes how digital filters can be classified by their use and their implementation. The use of a digital filter can be broken into 3 categories: time domain, frequency domain, and custom, really. As previously described, time domain filters are used when the information is encoded in the shape of the signal's waveform. Time domain filtering is used for such actions like smoothing, DC removal, waveform shaping, etc. In contrast, frequency domain filters are used when the information is contained in the amplitude, frequency, and phase of the component sinusoids. The goal of these filters is to separate one band of frequencies from another. Custom filters are used when a special action is required by the filter, something more elaborate than the 4 basic responses. And by the 4 basic responses, I mean the high pass,
low pass, band pass, and band reject. We shall talk about these filters in the coming sections. We shall treat them one by one. Digital filters can be implemented in two ways: by convolution, also known as Finite Impulse Response or FIR, and by recursion, also known as Infinite Impulse Response IIR. Filters carried out by convolution can have far better performance than filters using recursion, but execute much slowly. The next sections of this course shall describe digital filters according to these classifications. First, we'll look at the filters carried out by convolution. So let's get on with this. Let's take a look at each of the filters listed here one by one. Hello, welcome back. In this lesson, we shall take a look at windowed sync filters. So windowed sync filters are used to separate one band of frequencies from another. They are very stable, they produce few surprises, and can be pushed to incredible performance levels. These exceptional frequency domain characteristics are obtained, of course, at the expense of poor performance in the time domain, including excessive ripple and overshoot in the step response. When we design the windowed sync filter by the standard convolution, it is very easy to program but slow to execute. When we use something like the Fast Fourier Transform FFT, the speed improves. Let's take a look at this. Over here, we have the frequency response of an ideal low-pass filter. All frequencies below the cutoff frequency Fc are passed with unity amplitude. As you can see, all frequencies over here have the amplitude of 1, while all higher frequencies are blocked. So frequencies above Fc over here are blocked. The pass band is perfectly flat, as you can see. The attenuation in the stop band is infinite, and the transition between the two is infinitesimally small. In fact, it's almost as if there is no transition band in this ideal frequency response. So, taking the inverse Fourier transform of this ideal frequency response produces the ideal filter kernel. This is the impulse response, and this is what it looks like. This curve is of the general form sin x over x, hence it's called the sinc function. This curve is given by the equation h of I equals sine 2 pi fci over I over pi. Convolving an input signal with this filter kernel provides a perfect low-pass filter. The problem is the sinc function continues to both negative and positive infinity without dropping to zero amplitude. While this infinite length is not a problem when we're working with pen and paper solving mathematics, it becomes a problem when we're using computers to program this filter. So to get around this problem, we'll have to make some modification to the sinc function. We'll have to make it look like this. First, it is truncated to m plus 1 point, symmetrically chosen around the main lobe, where m is an even number, so we truncate it like this. All samples outside these m plus 1 points are set to 0 or simply ignored. And then the entire sequence is shifted to the right so that it runs from 0 to m. This allows the filter kernel to be represented using only positive indexes, because most computer programming languages don't allow us to have negative indexes. So we just do this shift. The sole effect of this m over 2 shift in the filter kernel is to shift the output signal by the same amount also. And since the modified filter is only an approximation to the ideal filter kernel, it will not have an ideal frequency response. So to find the frequency response, we just need to take the Fourier transform from the truncated filter kernel, and this is what the frequency response looks like. It looks messy, it doesn't look ideal at all. There is excessive ripple in the pass band, and there's also poor attenuation in the stop band. And we have these problems because of the quick discontinuity at the ends of the truncated sinc function. And also, even if we increase the length of the filter kernel, it doesn't reduce the problem. The discontinuity is significant no matter how long m is made. Fortunately, there is a simple method for reducing this particular problem. So there are different simple methods to improve the frequency response
created by the truncated sinc function. This image over here shows what is known as the Blackman window. Multiplying the truncated sinc by the Blackman window results in a windowed sinc function kernel. So this is what we get when we take the truncated sinc function, when we take the truncated sinc filter kernel we saw earlier and we multiply by the Blackman window, we get this new window known as the windowed sinc filter kernel. The idea is to reduce the abruptness of the truncated ends and thereby improve the frequency response. As you can see, this is the truncated sinc frequency response and this is the windowed sinc frequency response. There is a massive improvement. The pass band is now flat and the stop band attenuation is so good, it's almost perfect. Several different windows are available out there. Most of these windows, of course, are named after their inventors. The most useful of these windows are the Hamming window and the Blackman window. The Hamming window is given by this equation, Wi equals 0.54 minus 0.46 cos 2 pi I over m. And this is a calculated value. We have to use these exact values. And the Blackman window is given by Wi equals 0.42 minus 0.5 cos into bracket 2 pi I over m plus 0.08 cos into bracket 4 pi I over m. So these are the equations of the Hamming window and the Blackman window, where I equals 0 to m and m is the length of the filter kernel. The characteristics of the Blackman and the Hamming windows are summarized over here. The shapes of these two windows are shown in the image on top over here at the top left corner. We have the Hamming on top and then the Blackman below the Hamming. These two curves, this is the Blackman curve below here and then the Hamming curve on top here. Just bear with me, I know the screen is a bit saturated, so let's take it one at a time. This is all their characteristics put together. And the equations that we saw earlier are also given below. We have the Hamming window equation and the Blackman window equation. But what we are truly interested in is the frequency response, which is shown on the right hand side of the screen. On top we are showing it in the linear scale, and then below that we have the logarithmic scale using the unit of decibels. The Hamming window result is about 20% faster roll-off than the Blackman window. However, the Blackman window has a better stop band attenuation, about 0.02%, and Hamming has about 0.2%. And the Blackman window also has a lower passband ripple, as we can see. So that's all there is for this lesson, and if you have any questions, do let me know. And like I said, pause the video and just take a look at the images. I know it's saturated, I understand. If you don't understand this, it's also fine. We're going to write code to demonstrate this. Most people get all of these algorithms working without understanding any of these things that we're talking about. So I'll see you in the next lesson. Hello, welcome back. So to design a windowed sinc filter, we need to select two parameters. The first is the FC, which is the cutoff frequency, and the second is the length of the filter kernel, over here given the letter M. The cutoff frequency is expressed as a fraction of the sampling rate and therefore must be between 0 and 0.5. The value for M sets the roll-off. According to the approximation, M is approximate to 4 over BW. The length of the filter kernel M determines the transition bandwidth of the filter, and over here the transition bandwidth is denoted as BW. This is only an approximation since roll-off depends on the particular window being used as well. So like I mentioned, BW is the width of the transition band measured from where the curve just barely leaves 1 to where it almost reaches 0. This is say about 99% to 1% of the curve. The transition band is also expressed as a fraction of the sampling frequency and must be between 0 and 0.5. Right here we can see that the shape of the frequency response does not change with different cutoff frequencies. It stays the same actually. After we've selected FC and M, the filter kernel can be calculated from this equation over here. the cutoff frequency Fc is expressed as a fraction of the sampling rate, a value between 0 and 0.5. The length of the filter kernel is determined by m, which must be an even integer. The sample number I is an integer that runs from 0 to m, resulting in m plus 1 total points in the filter kernel. The constant k is chosen to provide unity gain at 0 frequency and to avoid things like divide by 0 error. Don't be worried much about the length and the complexity of this equation. You can identify some of the components that we've spoken about. For instance, the sinc function is over here, the m/2 shift, and then the Blackman window equation we spoke of is also over here. So for your homework, I want you to take this equation and try to break it into its various components based on the characteristics of the windowed sinc filter we've spoken about. Remember, we've spoken of the nature of the sinc function, we've spoken of the equation of the Blackman window, and then the equation of the Hamming window. You can identify all of those components in this kernel. Hello fellas, welcome back. In this section, we shall look at FFT convolution. In this very first lesson of this section, we shall look at overlap add. So there are many DSP applications where a long signal must be filtered in segments. For instance, high fidelity digital audio requires a data rate of about 5 megabytes per minute, while digital video requires about 500 megabytes per minute. With data rate this high, it is very common for computers not to have enough memory to simultaneously hold the entire signal to be processed. There are also systems that process segment by segment because they operate in real time. For example, telephone signals cannot be delayed by more than a few hundred milliseconds. In still another application, the processing may require that the signal be segmented. An example is the FFT convolution, which we shall take a look at in this section. The overlap add method is based on the fundamental technique of DSP, which is to 1. Decompose the signal into simple components, 2. Process each of the components in some useful way, 3. Recombine the processed component into the final signal. In this arrangement on the left, we have a 300 sample input signal, which we want to filter using the filter kernel on the right over here, which is a 101 sample filter kernel. This is actually a windowed sinc low pass filter. The key to the overlap method is how the length of these signals are affected by convolution. When an n sample signal is convolved with an m sample filter kernel, the output signal is n plus m minus 1 samples long. For instance, the input signal here is 300 samples, which, as we can see, begins from 0 and ends somewhere around 299. The filter kernel is 101, runs from 0 to 100, and the output signal, which we shall see later, is 400 samples, and it will run from 0 to 399. In other words, when an n sample signal is filtered, it will be expanded by n minus 1 point to the right. This is assuming that the filter kernel runs from index 0 to m. If negative indexes are used in the filter kernel, the expansion will also be to the left. Over here, in the input signals, zeros have been added to the signal between 300 and 399 to illustrate where this expansion will occur. This arrangement over here shows the decomposition used in the overlap add method. The signal is broken into segments, with each segment having 100 samples from the original input signal. In addition, 100 zeros are added to the right of each segment. In the next step, each segment is individually filtered by convolving it with the filter kernel. This produces the output segment shown below. Since its input segment is 100 samples long and the filter kernel is 101 samples long, each output segment will be 200 samples long. The important point to understand is that the 100 zeros were added to each input segment to allow for the expansion during the convolution. If we look carefully, we realize that the expansion results in the output segment overlapping each other. These overlapping output segments are added to give the output signal. This is what the output signal looks like. It's the overlap of the output segment 1, 2, 3 put together that gives us this output signal. This is the output segment. We've got output segment 1 here, output segment 2 here, output segment 3 here, overlapping.
If we put them together, we get the output signal. The overlap add method produces exactly the same output signal as direct convolution. The only downside here is there is a much greater program complexity to keep track of the overlapping samples. FFT convolution uses the overlap add method. Only the way that the input segments are converted into the output segment is changed. Over here in this arrangement is an example of how an input segment is converted into an output segment by FFT convolution. First, the frequency response of the filter is found by taking the DFT of the filter kernel using fast Fourier transform. Over here we have a simple filter kernel. It's a windowed sync bandpass filter. The FFT converts this into the real and imaginary part of the frequency response, as we can see over here. These frequency domain signals may not look like a bandpass filter because they are in the rectangular domain. They're in the rectangular form. Remember, the polar form is usually best for humans to understand the frequency domain, while the rectangular form is normally best for mathematical calculations. These real and imaginary parts are stored in the computer for use when each segment is being calculated. In the second row, we have the input segment to be processed. The FFT is used to find the frequency spectrum. As we can see over here, we have the input signal on the left and then the real part and the imaginary part of the frequency response of the input segment on the right. We use the FFT to find the real and imaginary part of the input segment. The frequency spectrum of the output segment is then found by multiplying the filter's frequency response by the spectrum of the input segment. The inverse FFT is then used to find the output segment from the frequency spectrum. It is important to recognize that this output segment is exactly the same as would be obtained by direct convolution of the input segment and the filter kernel. The FFT must be long enough that circular convolution does not take place. This means that the FFT should be the same length as the output segment. For instance, in this example over here, the filter kernel contains 129 points and each segment contains 128 points, making output segment 256 points long. This calls for a 256 point FFT to be used. This means that the filter kernel must be padded with 127 zeros to bring it to the total length of 256 points. Likewise, each of the input segments must be padded with 128 zeros. As by now you may be wondering why FFT convolution and not just the standard convolution. Well, depending on the length of the filter kernel, FFT convolution becomes massively advantageous. This graph over here shows the execution time required by FFT convolution and the standard convolution. We see that for standard convolution is directly proportional to the number of points in the filter kernel. In comparison, the time required for FFT convolution increases. In comparison, the time required for FFT convolution increases very slowly, only as the logarithm of the number of points in the filter kernel. The crossover occurs when the filter kernel has about 40 to 80 samples. So this is the takeaway message. For filter kernels shorter than 60 points, so this is the takeaway message. Filter kernels shorter than about 60 points can be implemented faster with standard convolution, and the execution time is proportional to the kernel length. Longer filter kernels can be implemented faster with FFT convolution. With FFT convolution, the filter kernel can be made as long as we want, with very little penalty in execution time. For instance, 16,000 point filter kernel only requires about twice as long to execute as one with just 64 points.